Hello, can you hear me? Nice. Yeah, welcome to FARM. It is a great honor for me to be the first talk, so us to be the first talk of this great workshop. It's been my dream for many years to come here. So Eliana and me will be talking about our experience with using functional programming with real artists. Yeah, so talk about experience and also give you a little demo of the stuff we did. So Eliana is a student, or was a student until recently, of my master's student, and both of us work at the OST. Maybe some of you know the OST. It's a university in Eastern Switzerland, one of the major universities in Eastern Switzerland. Maybe many of you know it from Zurich, which is an event that takes place there that we co-organized for the last 8 years. So who's been to Zurich? Wow, nice. For those of you who haven't, please, I welcome you to please join. It's 3 days. It's free for participants, and we have a lot of fun there. Good, but these aren't the only two people involved in this work. So actually, the people in the center of this work are two artists who you see on the screen right now. This is Soren Kors and Partner Gao. They are quite popular in the art scene because of their robotic artwork. So they make a lot of art that moves around. And one of the specialities that they have is that these artworks have a certain, or they sort of give a certain emotional state to the person who's seeing it. But better than me talking about it, I'm going to show you a little video that they have. I'm going to put my microphone just 1 minute.
The next work is a sound-sensitive installation that we affectionately call the Beans. And we wanted to work with the notion of being surrounded by a tribe of very shy, sensitive and sweet creatures. So how it works is we have these panels which we have on the wall, and behind them we have these little creatures which hide. And as soon as it's silent, they sort of creep out, and if it's even more silent, they stretch their legs out, and at the slightest sound, they hide back again. So we had these panels on 3 walls of a room, and we had over 500 of these little pygmies hiding behind them. So this is how it works. It's a video prototype. So when it's quiet, it's sort of coming out from behind the panels, and they hear like humans do or real creatures do. So they get immune to sounds that scare them after a while, and they don't react to background sounds. You'll hear a train in a moment that they don't react to. But they react to foreground sounds. You'll hear that in a second. So we worked very hard to make them as lifelike as possible. So each pygmy has its own behavior style, swings, personalities, and so on. So this is a very early prototype. Of course, it got much better after that. And we made them react to people, but we found that people were being quite playful and childlike with them.
I met Partner Gao and Soren Kors many years ago, I think about 6 years ago, and I was always thinking, wow, this is really great artwork. And I sort of asked them, what's the engineering that goes behind this? And I was surprised to see that a lot of the stuff they do is at a higher level than what most engineers do. And I was thinking, wow, this is really complicated stuff. And I asked them, was this easy to do? And they said no, and they were struggling with it. And this is quite natural, right? Because this is a lot of low-level work. There's a lot of low-level hardware work. It's all in C, or it was all in C some time ago. Yeah? And so all this is written in a very low-level imperative style. But they have so high-level behavior intertwined with this low-level code. It was getting really hard for them to maintain, really hard for them to write. And so over many years I was thinking, let's do something together that sort of gets people out of this misery. So this was the original motivation for this work. So artists have a very strong aesthetic drive for beauty and elegance in their work. Since we're in Milan, I chose these pictures to depict that. And so there's a little parallel to this. So there's functional programming, that's what we're here for. There's a style of programming where elegance, simplicity, and clarity are really highly prized. And so if you take this logic a bit further, it's not implausible to say that all artists should then be functional programmers. But they are not, right? Why are they so reduced to writing this low-level imperative code? So this was the main curiosity that drove me to start this book. And because of the position that I am in, I can use students, or abuse students to explore these curiosities. And so, yeah, so this is the topic of Elian's master thesis. But this is not all. How many of you know this really great textbook for learning Haskell? So the Haskell School of Expression. Yeah. So I think that's really good. It was really great. It's learning functional programming through art. Right? That's really great. And also, the very reason that we are here at this workshop, at the farm workshop, is also evidence of the fact that there is a lot of synergy between art and functional programming. You can ask, how many of you are artists? Whoa, nice. Yeah, so that was how this was started. So in this work we try to use functional reactive programming, and we try to see how well artists accept this form of programming. So FRP, I guess most of you know this, but just a one-line summary of what that is. FRP is a style of programming for implementing reactive systems using the principles of functional programming. So it started almost 30 years ago. So there was an ICFP paper in 1997 from Conal Elliott and Paul Budak on this. This was pretty much, very groundbreaking at the time. And it had some very nice ideas. So to make time explicit, have some basic building blocks that you can combine using nice algebraic laws. It had very nice stuff. And so this paper created somewhat of a revolution and led to a very large number of further attempts to do FRP. To some dissatisfaction of its first author there, who has since moved on to write some of the greatest papers in this area anyway, so in our field. But yeah, so this was the story. But I didn't see any artists using this, so I was thinking, maybe we could sort of bridge the gap. So, yeah, so now I'd like to ask Elian to show you some of the special things of the artworks that we did. So we did a number of artworks with them. Elian's going to talk about the edge beings right now, which is one of their newer artworks, but we've also got one of the pygmies what you've seen. So it's not called pygmies anymore, it's called Untitled, because of some reasons. But yeah, Elian, please.
Thanks. So I would like to introduce you to the artwork Edge Beings and show you some insights in code design using FRP in Haskell, and talk about impressions of the artist about her work. So you can see here a sketch of Edge Beings. This is an artwork consisting of panels that are mounted to a wall, and you see these black shapes that are creature living behind these panels. The idea of the artwork is that if you are observing it, you will observe some social dynamics between these beings. And these beings belong to groups, and only one group is allowed to be outside at a time. And each group has a suppressor, and if a suppressor is stronger than the current group that is outside, the group has to hide, and the suppressor on its own can emerge. There is also a motion detector sensor, so if you're stepping too close to the artwork, the beings are aware of your presence and they start to hide and just peek over the edge and hide again until you step back. In an imperative style, you would typically send commands to the motors, like go from the hiding position to the peeking position or something like this. But in effort, we use another approach, which is typically for FRP, where you build signals for each being containing the current position of the being. So this position is sent continuously to the outputs, to the motors. So if a being should stay at the same position is sent again and again. And if being should move out, for example, the position is increased step by step and sent to the blockers. There's also an input signal containing the data about the motion detector events, which then changes the behavior. The artists usually use a Raspberry Pi that controls all the panels, and they have a framework called Atlas in Python, which controls normally also the behavior, but in our case now just motors and sensors. So we just added a Haskell service which runs the FRP code written in Yampa in Haskell, and there are this behavior that is started and produce the positions. Then we send the input data of the sensor over a WebSocket to this behavior and gather it into a signal, and then the output positions are sent back to the motors, to models which use the motors. And this design also allowed us to replace the physical hardware with simulation because it's decoupled, so it was really easy to just connect something else to it. The simulation enables testing without access to the physical hardware. And you can see it here, it's a pretty simple web framework, web UI. And you can see there are also parameters where the artist can test out some different behaviors and see the reaction immediately on the screen. So let's have a look at the simulation. You can see here the social behavior of the beings. So at the moment one group is outside and the others peek over the edge of the light again. And now at the left you see the suppressor coming out. Now it emerges and the other have to hide. And now the group of the suppressor is allowed to come out, and the other wings just peek over the edge and hide again. The architecture also enables an immediate reaction to the parameter if you're changing the parameters. So normally you would, in imperative style, you would send a command and move from one position to another. So it would be really hard to change this movement during the movement. And with artist architecture, it's easy because the position will just increase if you increase the velocity. You can see it here. Maybe focus on the beam on the left side. So it will start really slow, and when the velocity is increased, it increases the velocity immediately. But when we look at it again, it's being on the left side. The others also react to it. You can see it very clear. So that is so let's have a look at our code or at the design. Big advantage of FRP is that it makes it really easy to write code that is close to the problem description. So for the being behavior, this would be that you have the social behavior of the being, and when a motion event appears, the behavior changes to disturbed behavior, and if there is no motion, it will change back to the social behavior. You can see it here in the code written in Yampa. So we start with the social behavior until a motion event happens, then the behavior switches to the disturbed behavior, and after no motion event, it will switch recursively back to the social behavior. Let's have a look at the social behavior. This is different depending on the role of the being, if it's a suppressor or a normal being. So for the suppressor, it looks like this. The suppressor just has a check behavior, which means it looks over the edge and hides again. It does this until it has the highest rank of all that are things that are outside. And then it will change the creep out behavior and is allowed to go to the standing position. If nothing happens, the suppressor will hide again after some time, but other groups are allowed to come out. Or if there's a higher rank, not higher rank event, because someone else is coming, it has to hide too. For the normal beam, it's similar, so it checks until its group is allowed to come out. And then if the group is not allowed to be outside, it will change back to the check behavior. After we tested our code in the simulation, we also were able to test it on a physical prototype. You see here the social behavior. These two beings belong to one group and are peeking over the edge. Because they are the only group, they emerge to the standing position. And now at the top there's a suppressor coming out as soon as it emerges the other after. And now they're just allowed to peek over the edge until the suppressor is gone. We also implemented the steer behavior when a motion event happens, but the physical prototype doesn't have a motion sensor yet, so it's here just a key press. But you will see as soon as the key press happens, all of the beams have to hide. They should just peek over the edge. Now they hide. Just peek over the edge. The modular architecture that we used enables the simulation, which uses the same behavior code as the hardware, and this enables testing, which is an advantage for the artist. And it also makes it easy to switch between the different hardware setups. For example, you see here another prototype which looks like the untitled hardware that I saw in the beginning. It's working like that, but it should be only one region that peeks over the edge at a time. And now we connected the edge beams control software with it, and it doesn't matter if it has a sound sensor and different motors, it also works the same. So you can see here, one group is outside, and on the bottom the suppressor appears. And then the being on the left has to hide, and on the right the being is about to come. Another advantage is the code, because it's more understandable than the artists are used to from the imperative style that they use. They were really impressed that it's possible for them to read the code and understand it. This is because it's close to the problem description. And they told us that this is an improvement for them because at the moment they have to tell the developers what they want, but they cannot control what they did because they are not able to read the code. And this style of coding can improve the collaboration between artists and programmers. If you are interested in our work, we have 2 papers in proceeding, an experience report and a demo paper. The experience report also contains more insights into the code. And yeah, for us, we saw that FRP offers many technical advantages for programmers, but at the moment we don't think that it's possible that artists program it by themselves. The problem is that you need an understanding of FRP and, for example, Haskell to code with it. So there's a need for interfaces that hides the complexity from the artists or from people that are not very experienced with programming. But better collaboration is possible between artists and programmers. For example, we would recommend a pair program so the artist can tell what he wants or what she wants, and the programmer can do it.
So we started this work with the aim of observing how well real artists would accept programming in this style. And at the end of this work, we think that it is still possible to keep the dream alive, and that functional programming may one day allow artists to express beauty and elegance, not only in their end work, but also in the code that runs this end work. It's like a scientific engineer, I was talking to him just before I came, he said, conquer the world through beauty. And I think that's a nice note to end this talk. Thank you very much. Yeah.
So the previous artwork, the one we
one second straight, there's the mic coming here.
Oh, sorry. Yeah. So the previous artwork, the one with like the spoon, so that one is impressive to youngly. And was that one written by the artists themselves, or was there a similar collaboration with the program?
Yeah. So the initial artwork, which used to be called Pygmies, then Islanders, and now Idol, that was already written in a low-level C language. Our first collaboration with the artist was to duplicate the behavior using FRP.
Yeah, I know, but my question is that one, like before you guys even talked about
yes.
that one, did they, the two artists, did they write that software on their own without any programmer collaborators?
Oh, I know, I think they had help. Yes, I'm not 100% sure, but they did have help.
They have a developer team that goes for them.
Ah, okay, because I was going to say that in some sense to step backward, you suddenly you need a programmer, and before that they could just hack it together themselves, but then, okay, cool.
Yeah. Are there any questions? Other questions?
Sorry, I think I'm going to interrupt while we have more questions. I do not hear my phone because this is not going to be broadcasted, but it's on remote viewing. Do you have a demo portion after this, or is this conclusion for the whole slot?
This is the whole slot, yeah.
Well, please do continue your questions. I'll also just say we're going to take about a 3-minute additional break after this talk to see if we can get the audio issue resolved.
Thank you, ma'am.
Very cool work. Thanks. It's kind of a broad question. So I see this as could be seen as an evaluation of the beauty of Haskell's method. So we use these oracles, these artists who are really good at judging beauty and quality, into judging now these function programs. I'm wondering if we can do something the other way. So get feedback back to them, so we can improve our images. We can somehow make them even more beautiful.
Yes. Yeah, that's
what are your thoughts on this?
No, that's a very good question. Yeah, that is a very good question. So till now, the artists actually, they always said that we like something graphical. Somehow they're really into having it graphical. But I've always thought that, hey, of course, there's only so much you can do with a graphical interface, right? And I'm thinking that, then we sort of make our box and they have to live within this box. And I think that using a textual, sort of algebraic way of doing things just opens up the freedom into all this. But somehow I think we do need maybe better tutorials, maybe a language which is more suited. But yeah, this is a very good point, that maybe we should try to mold our languages from their perspective as well. Yeah. And of course, there's always this also, I don't know why, but there's this sort of inherent tension between artists and mathematics and algebra, not everywhere, but this is something that we did face, right? They said that overall, the moment you say the dirty A or algebra, people get a bit upset. Yeah. So we have to go to this a bit slowly. Yeah. They have had many years of bad experience in school. Thank you, that's great.
I'm afraid this is more common than the question. So, first of all, errorized DSLs do lend themselves to graphical expression, right? We've done projects completely outside the artistic domain, but that might be something to do. But generally, it seems you seem unsure of what user group you're trying to target, right? And in a lot of arts that have artifacts associated with them, right, there's the artist herself, and then there's some person actually implementing or building the thing, right? So I've noticed that working in stage lighting. We also had from today's Gazelle, where I came to the conclusion that it was unrealistic that the lighting designers would actually use the language, but instead that it would have to be somebody else. And the work might be a little more effective being focused on one group or another at this stage.
Yes, I understand. At the end, this is the conclusion we came to as well. I said that, okay, now at this point in time, we need something like a air program, and both of them are on the same page, and say, okay, I will just easily does that. But the distant dream is that maybe not. I don't know.
But is this really desirable? Right? Is this really what we?
Yes.
I'm not sure of that, right? That's really what
Yes, very valid. Yeah.
Any more questions? One last one? Let's thank the speakers. I believe that next up we have Mario Desires. Excellent. And you need to project audio to the room.
Sorry?
Do you need audio? Great. Off you go.
Okay.
Exact question about that.
Yeah, that's one. Let me just give you the microphone.
Yeah, so with Tidal, we have managed to get lots of musicians using Haskell with the DXL, so it's possible. But just push back on the idea that artists or about having a lot of beauty. That's not my material.
Same. Oh, thanks. Was it enough then?
I remember we did that for a farm concert, we did the call that include beauty. Go on that outside. Or push back.
Well, I was plugging in. This says, hi, I'm your name. I'm the general.
Okay, great. So, hi everyone, and thank you for being here, or at least connecting to here. And of course, thanks to May for inviting me and helping me to shape my ideas. What I'm going to talk about is my, let's say, personal experience as, among other things, I'm a coder and I'm a painter. I'm here in Milan, and this is kind of a personal research project that I want to share with you. So, we're going to talk about tessellation, and I guess how many of you knows about tessellations? Okay, so and I will have a very, very basic and visual, because I'm a painter, crash course on tessellation, so we know what we are talking about. And the basic is, we are, tessellation is a way of covering a space, a 2D space, to make it simple, with tiles. So it is tiling. You have one or more, let's say, unit repeating, trying to cover And here you have some hexagons I sketched, because as soon as you think about tessellation, I mean, when your mind, at least my mind goes, okay, how many tiles? Is there a regularity? Is there a period, pattern? Is there something I can do to change and find some new things, some new vision? And one interesting point to be made is that tessellation could be infinite. I mean, you can cover the plane periodically, the whole plane. Of course, this is an abstraction, because in reality, they're always talking about finite tessellation. But if you think, I mean, it is easy to visualize how the tessellation can continue forever. And this is one of the reasons why tessellation has been found in human history before any, let's say, formal math definition. Because this repetition, large repetition of very small unit elements, is a kind of direct, very powerful visual approach to the concept of infinity. So, you wonder, I mean, you see that you could fill the whole space and take the whole time to do so. So, it is a kind of, let's say, visual cue to something very, let's say, powerful and moving inside us. Infinity. And personally, I mean, I could feel a very strong personal bond to the craftsman, artisan, philosopher, I would say, that built this floor 2,000 years ago in a Roman villa in Coimbra, in Portugal. I mean, this is beautiful and moving. Of course, and this is, let's say, the last slide in this very brief course, I mean, tessellations comes in a variety of shapes, and we're not bound to polygons. I mean, here you have edges, parabolic edges, cures, and very, very, let's say, complex things can arise from, let's say, simple tiling. I took this example for two reasons. One, it is beautiful. I mean, these are just two tiles put together. And the other is that this kind of tessellation has been discovered in the 70s by Roger Penrose, so mathematician, physicist, and by the way, a Nobel Prize winner. So, I mean, we can stay, I mean, it's a comfort when we sketch our little things, I mean, we are in good company. So, then, these are tessellation, and let's say, the first, I mean, one side of my research is writing software library in Scala, in functional style, and it is a free resource, it is public, and you can find it on this website, and it is freely available. It's a work in progress, it welcomes, of course, let's say, contribution, and it is interesting for me that Scala has quite a large footprint in terms of diffusion, so you can port it to Java, to JavaScript, and if we have time, I will show you a little bit of JavaScript. What is the goal of Tessella? By the way, Tessella is the Latin name word for small tiles. So it is also the English, the root of the English word of tessellation. So I thought it was a nice name for the library. The purpose is to provide a toolbox of functional methods that deals with finite tessellations, and restricting ourselves for the time being to the most classical form of tessellation, which is tessellation made by regular polymers. So using just a square, a regular triangle, and so forth. The main, let's say, point behind the library is that tessellations, finite tessellations, are described as undirected graphs. And so every tiling is an undirected graph, which is a powerful way, computational model, to deal with these objects. Of course, not every undirected graph is a tiling. So this is where things get mathematically, let's say, a little bit complicated. In this example, of course, 3 square and a regular pentagon cannot exist in a regular tessellation, because the vertex configuration at node 5 is more than a full circle. And so this is let's say, a nice graph, but not a tessellation. And we have to factor in also spatial requirements, because this could be a tessellation, but it is overlapping. So once again, it is not okay. So in Tessella, we provide, let's say, a validation check and functionalities to, let's say, check the validity of a regular polygon tessellation. And the milestone so far is that we have transformation functions that allows very basic functionalities, like adding or removing one regular polygon at a time. And we can test the quality among finite tessellation, but they mirror it, the labels are different, fine. We know that they are the same. And of course, there is a good wealth of creation algorithms. One line of code creating complex things from basic primitive methods. And we have conversion to visual, because as soon as your undirected graph gets a little bit complicated, you lose sight of what is the visual of the tessellation. So, nice transformation to SVG and conversion to graph description languages, so you can have your graphs factored by other application. And let's say testing of values of the tessellations that can help us in our, let's say, search methods for interesting things. The main point for me on the artistic side of the research is being able to write this basic transformation function, because these are, let's say, what I needed to start experimenting with random things and, let's say, feeding methods to see what happens without having to start from, let's say, describing a pattern, but making a pattern in the way. So I needed methods to say, I want to deal with 5 things, I want 5 squares or 100 squares. I want to describe this mathematically, having a computational model, so I can add one another polygon and see what happens. But the toolbox is there. I mean, it's there for mathematics, it's there for whatever you want. For me, the direction, I mean, my sensibility was art. So I was interested in seeing new things and seeing how they could develop. So these are the kind of painting, acrylic paintings that I do is completely, let's say, different realm from coding, because I stopped coding and I started doing things. It is hard work because I try to stay, in coding as digital as possible and in painting as analogic as possible. So I get my pencils and compass and I sketch and paint. And that's, it is satisfying work, also it is kind of meditation work in the process, and I'm pleased about the results. I like what I do. But what I wanted in this realm of regular polygon tessellation, I want to give you a little bit of, let's say, the research path that I went through. For my sensibility, there was a problem of scarcity, because the fact is that when you enter irregular polygon tessellations, there are just 4 regular polygons that completely tessellate the whole plane. And one of them, the 5th, is the octagon, and it appears only in one tessellation. So you find yourself more or less here. You have all the 4 polygons. It is squares, triangles, hexagon, and dodecagons, cross-sides polygons. And this is the kind of, let's say, unicorn in irregular polygon tessellation. You have just 7 of these tessellations where you have 7 classes of symmetry with 7 different vertex configurations. I don't know if you see it, but each vertex is colored with a different color, and each different color is a class of symmetry. You can move the tessellation from one color to one color, and it remains the same. But you cannot get more complicated or beautiful than this. And for me, it was a kind of boring. I don't like to paint this, okay? I'm going to make that. So I went for using, let's say, more variety of polygons, even knowing they don't fill the whole plane. And so I started playing with randomic growth. First with polygon tasks. So what if I take pentagons and decagons and grow them? And then I started putting more constraints. So what if I take pentagons and decagons and I want vertex configurations? And things starts to appear, and then you have the artistic limit. You take what you feel is right for you, and I think as an artist that you are allowed, let's say, freedom to bend the rules. So this is not more a regular polygon tessellation, even though it is a tessellation. And if you think at gaps as regular polygons, we are still in the realm of tessellation. It is not a regular polygon tessellation, but it's nice to me, so I painted it. And so I went on, and these are more examples for this. And that's it. That's my research, my pet project, and let's say my fun pastime when I have time. And I'm happy that I've been able to share it with you. And of course, if you have questions now or afterwards, I'm here for you to answer.
Thank you. Have you tried
frontier between polygons. And in your case, in particular, you end up, I mean, that's basically how you construct the style of tessellation that Escher uses, for instance. Have you tried experimenting with that?
No, not yet, but I mean, in terms of coding, we are talking about functional codings, and once you start seeing tessellation as graphs, it is just a matter of which constraints you want to apply to a graph in order to get, let's say, different classes of tessellation. So that's definitely is a kind of research path that could be followed.
Thank you for the talk. We were talking before about more possibilities for the development of the cell, and I talked on another one that might be interesting. Do you know the work of MCH? You probably seen this tessellation of the circle. Then if you allow in abstraction for the space to have some kind of curvature, then you can play like you can have an heptagon tessellation, which would be really fun. And I think the representation might be as well, because you are when you see the graph is like abstract from any kind of distance notion, so you could still have the same representation and start, I don't know exactly how, probably play with curvature of spaces.
Yeah, definitely. And also, I started experimenting also on, let's say, 3D tessellation, so feeling of the 3D space, and that's again, it is something very interesting artistically. I have some ideas of, let's say, sculptures that could be 3D printed, that is very digital, or could be handcrafted. This is very logical, but very stuff as well.
And just a quick technical fast question, like when you output image, what kind of control you already have on the position of the image, maybe the colors you have?
Okay. I don't really have time, but I can, let's say, show you a little bit. I was talking about, let's say, JavaScript. So this is a very, very, let's say, primitive JavaScript, let's say, things derived from the library. I can randomize, and in terms of control, I can decide, I mean, it is just an SVG file, so you have all the control you want, but you can hide, put, let's say, randomize again, and this is it, or I can say give me 20 of that, randomize again, and that's it.
It actually wasn't the mic's not for the room, the mic's for the people on the project, so it needs to be a little higher.
Okay, okay, sorry.
We have time for one last question. We started 15 full minutes, like we're not going to worry about running to break.
By the way, this is fantastic, unbelievable. I don't know if you can quite see the shirt, but this is actually a minimum spanning tree of an aperiodic tiling done by Dr. Edmund Harris. So my question is, do you have collaborators in tessellation, Tesla, and things like this? Are you looking for some?
Not really. I mean, I'm looking for contributors on the library. I mean, definitely, in terms of, let's say, spreading the beauty, I mean, I'd love to have, let's say, collaborators and peers. And that's one of the main reasons I decided to step up and come here. I mean, to meet like-minded people. So if you're interested,
great, yeah, we should talk more after this. That's his specialty, is tessellations, tilings, aperiodic, things like that, bringing that to 3D, and There's much more to it. This is fantastic.
Great.
What a wonderful note to end on. Let's thank the speaker again. So we're probably going to go about 6 or 7 minutes into the break. We're not going to worry about this, but it will get extremely noisy in the last 5 minutes of your talk. And the other people are going to go to break too.
So we'll have like visuals for the noise and stuff.
Yeah, it sounds great. We'll put a microphone out there.
Yeah.
I should also note that we might be back late from the break, depending on how hard it is to get our audio working. The next session does require audio. So you just be ready for that.
Looks like something's.
Yes.
Hi everyone, thank you so much for having me. My name is Yoni. For the artists here in the room who are disguised as academics, my artist name is Finnish, and I'll be presenting Hydra FCS, which is a extension to the Hydra video synthesizer for creating visuals with algebraic geometry using curves and surfaces. So Hydra, which was developed by Olivier Jack, is a web-based tool for live coding visuals. It's written in JavaScript, which is not a purely functional language, but Hydra itself is written in a very functional way, and that visuals are created just by composing functions together. So I'll give a quick example. So here we just have like OSC, which is short for oscillator, and we can scale it, we can rotate it with time, and we can even modulate it with other textures like noise. And the functions in Hydra are named in a very intuitive way, and it's very easy to compose them together. Olivier, the creator of Hydra, was very inspired by analog video synthesizers like the one on the right, and she sees functional programming as a way of translating these properties of modular analog synthesizers to code it. Sort of just like wire modules together to create different visual effects, and that's kind of what's happening with the code. So Hydra FCS extends Hydra by adding functions that correspond to equations for curves and surfaces, which are the subject of algebraic geometry. And it primarily incorporates equations for curves and surfaces in 2 and 3 dimensions, like relatively simple ones like circles and tori, or more complicated ones like epicycloids or wine glass. So we are in Italy, so if you forgot a wine glass, you can just use algebraic geometry. There are also some, it also incorporates some more complicated 4D surfaces. And so the question is, how do we, what are these equations that we're talking about, and how do we use them to create visuals? So to answer this question, I'm going to ask you a question that I often find myself wondering about, which is, what is a Friday? And I think there are at least 2 ways of answering this question. And one of them is by describing a procedure for creating it, for frying an egg. So you heat a pan, you put some butter on it, you crack an egg, etc. So then you observe what you've created afterwards, and you say, okay, well, I guess this is fried egg. The other way to describe fried egg is by its properties, right? So its texture, its color, its flavor, etc. So these 2 paradigms sort of correspond to parametric and implicit representations of geometric objects. So for parametric representation, you're describing a procedure for plotting a set of points and equations for where to plot those points, and that's a generated object. And an implicit representation uses sets of relations for where these points are, and it kind of just creating an object with by describing the relations between points and properties of the object. And so to understand the maps that are involved in creating visuals in Hydra, so you have a computer screen which we represent as a 2D space. And we want to map every point on the screen to some color. And so the two color spaces that we're currently working with in Hydra FCS are grayscale color space, which is analogous to one-dimensional line segment where one end is totally white, one end is totally black, and RGB, red, blue color space, which is analogous to a cube where each axis corresponds to the red, green, and blue. So when we're making visuals, we're trying to find interesting maps between screen space and color space. And what I'm hoping to show you is that algebraic geometry provides a treasure trove for these kinds of maps. So going back to the fried egg analogy, how do we describe a circle? And what properties do every point on a circle share? So every point on a circle, one of the central properties of a circle is that every point is an equal distance away from the center, in this case, the origin. And all of these points satisfy this equation the points x, y satisfy this equation x squared plus y squared equal 1. And so we can describe this as a function where all these points are solutions to this function of x squared plus y squared minus 1. And we can translate this to visuals by basically coloring different points on the screen by their distance from the circle. So this function basically tells us how far you are from the circle. So if the result is 0, then that means the path is on the circle. And in Hydra FCS, the way that this is basically exactly what happens, where let me just start to type with So here we have this animation where basically every point is colored based on how far it is from the circle, along with some sort of animation for time. So it's sort of intuitively named with I-circle. We also have other types of curves, like cardioid, spiral. We can add these together. So add a circle to a spiral. So the other approach is through the parametric approach, which is how would you describe procedure for drawing this circle? And so the way to do this is you have you set a control parameter, which we will call A, and you trace out the points of x and y, cosine A and sine A for A between 0 and 2, 5. And this is a map from one dimension, A, to 2 dimensions, cosine of A and sine of A. So we're basically using this as a map from grayscale colors, one dimension, to screen positions, 2 dimensions. And the distinction here from the previous case with implicit curves, which with the implicit curves we're actually sort of explicitly visualizing what the curve looks like, whereas here it's sort of more abstract, and we're using the parametric curves as a way to modulate position. So we have some input texture, like here, for example, circle, and we take the positions and also the color, the grayscale color we get from this circle function, and we use that to get a new position, and then we can put that into a circle, back into a circle. So if we go back to the visuals, so we have this spiral, and we have a function of circle, and we use a parametric curve for a spiral to modulate a spiral with a circle. And then we can kind of keep doing this. So we can then modulate the circle using a parametric curve for an asteroid, for example, with an implicit curve for a cardiac. And so we can kind of combine these in a bunch of different ways to just kind of keep going down. So to review so far, implicit curves define a curve based on its properties, and they, in our case, map from screen positions to grayscale colors. And parametric curves, they describe curves by constructing them procedurally, and they allow us to map from grayscale colors to screen positions. So now we can move a step further and move on to surfaces. So here we're going to start by the parametric representation. So what is the procedure for drawing a torus? So the way that you draw a torus is you take two interlocking circles and you trace one circle around the outside of the circle, around the outside of the other circle. And to describe this mathematically, we need two control parameters. So u and v, which each will trace from 0 to 2 pi, and we'll just plot all of those points. And so this is a map from two-dimensional space to three-dimensional space. So we can take our screen positions, and we can use equations for parametric surfaces to map them to RGB colors. Yeah, so like here's kind of a visual example. So we can map various points to from the screen space to the RGB cube in various ways. And the parametric surfaces allow us to do. So I'm going to switch this function for a spiral with a function for torus. So you can see that it's kind of switched from grayscale to RGB. We also have functions for spheres, a handful of them, you see in the documentation, which I'll go to later. Mobius strip. You can also incorporate existing Hydra functions, like collide, which stands for kaleidoscope. P. So there's also an implicit way for describing surfaces, which is by having some sort of equation for satisfied by all of the points on the surface. So an example of the sphere is if you have a sphere radius r that's centered at the origin. The sphere consists of a set of points that are the same distance from the center, which so they all satisfy this equation where x squared plus y squared plus z squared equals r. And so then we can sort of create a function with this equation where you can take three-dimensional points and plug them into this function, and you can say, okay, how far are you from the sphere? So the points that get a result of 0, you say, okay, those are on the sphere. If they're greater than 0, it's outside the sphere. If they're less than inside the sphere. And so this kind of gives us a map from 3 dimensions to 1 dimension. So it allows us to map from RGB colors to grayscale colors. So going back to the visual here, we have this RGB texture. Let's say we want to map back to the grayscale texture. We can use an implicit sphere. And so we're not just, it's not just like mapping from RGB to grayscale, but it's also kind of doing some funky things with the texture and whatnot. Switch this from sphere to cube. And there are a handful of functions for implicit spaces as well, so it kind of lets us map from RGB space to grayscale space.
Excuse me, are you taking questions?
Yeah, I mean, I'm almost done with it if you want to ask questions. So to kind of conclude, this provides an alternative paradigm for visualizing curves and surfaces to sort of more traditional plotting. So rather than kind of explicitly, literally plotting these curves and surfaces, we're kind of providing an alternative way of visualizing them. And seeing curves and surfaces as not mere geometric objects, but as functions that can interact with each other. And I think it teaches some sort of overlooked but essential concepts in mathematics, which are that there are often many different ways to represent mathematical objects. So a square, for example, you represent that as a graph, or as a group, or as a function through space and time. And so kind of taking these objects and showing different ways of representing them and interacting and having them interact with each other. And I think one of the great things about math is that is when we can have interesting things happen when we get distinct objects to talk to each other. So you have all these different fields in mathematics, but it's always cool when you have ways of bridging various fields and creating maps between different functions. So that's sort of what I hope that's one of the things that the school can sort of get across to maybe some people studying math regardless. And then lastly, if you go to the GitHub for HiRCS, there's a short tutorial there. Thank you.
If you go back to the last slide where you have the definition of f, yeah, just here. So what you have here on that line is the definition of the function in three parameters, x, y, and z. That's not an equation of a sphere. When you define the sphere implicitly, what you're doing is you're setting the right-hand side to 0, and you see that that's a locus of points. Right? The solution of those points, x squared plus y squared plus c squared minus r equals 0. Those points comprise the sphere.
Yeah.
Do you see?
Yeah. Yeah.
So the 0 is missing there.
No, this is the boundary definition.
So I'm saying that like this. So I'm saying that like the sphere is the solution to this. Yeah, I think like maybe the wording was.
No. This is what you have here is a definition of a function. Yeah. The solution to the equation is when you set something. You set this.
Yeah, when it's 0. Yeah.
Yes. So that part is missing. You're going to confuse people that way. Obviously.
Yeah.
Lots more questions, George.
Yeah, just have a quick question. So you're showing us these equations where there's x, y, just space, but the animation also has time over there.
Yes.
So I'm just wondering how this time factor in the animation of the equations.
Yeah. So basically, what happens is there's like a fract function, which is kind of just like mod 1. So you take whatever value you have, and you do mod 1, and then you subtract time from that. So that's kind of the way that the time is. Talk about that in the paper, but
So this is very cool that like seeing similar stuff for sound effects and graphics. So it's very fun to see this. I was curious, a lot of stuff you were doing was related to just like do something and then compose it in some other thing like that, which was like transformations of different spaces. I was curious how much functionality there is for like
kind of other parameters that like don't necessarily correspond to just string composition, but like I don't know quite what this would look like in graphics, but like you could use like weird things like volume to modulate like frequency and sound and stuff. Is there like similar kind of stuff, or like modulating frequency of some curve based off of something?
Yeah, I mean, I'm not sure if this answers your question, but I have been thinking a lot about how to connect it to sound, and that, like, sound, like, you can represent sound in a lot of ways, but one of them is kind of as like a one-dimensional stream, like audio and time, and so you could have the sound be like an input to a parametric curve and use that to modulate a visual. You can also potentially go the other way around and use visuals to generate sound. Yeah, does that, not sure.
I guess I'm wondering, like, are there any like, functions in Hydra/Hydra FCS that like kind of do that similar thing of like using one space to modulate another function in a way that like doesn't, like it kind of seems like a weird way of using it, if that makes sense. And I don't know what an example would be, so I can't really give one, but
like using like one space to modulate another space in like a way that wouldn't be like expected, I guess, or like you could, I mean, you could use like grayscale textures to modulate like RGB, like the functions for like for example the parametric curves, like they don't like you don't need to have an input of the grayscale texture. You could have it as like RGB texture instead, or you could have like various Hydra textures that like kind of come into like just really any like a video, for example. So it doesn't really require purely mathematical texture like that.
This is going to be our last question.
Most of what you showed was using position on the screen as input to your observations. So this is using 2D. Can you have other inputs? So you talked about time. So you could use the 3D to 2D that you have all in 2D. You could have position of the cursor or things like that. And you try things like that.
Yeah, I mean, so
to have more inputs.
Yeah,
those small dimension.
Yeah, those kinds of things would certainly work as like parameters. So, like for example, like each of the functions has various parameters, and so you could like have one of these parameters be like the sound, for example. With the Hydra functions themselves, like they're kind of abstracting over shaders, and so like those kind of need like a 2D sort of texture as like input. But yeah, so like for example, like you have like one of these parameters be time. Yeah, so I mean that kind of changes it. But yeah, so you can like have the parameters of these things be one like just whatever parameter or input you use or want to use.
Okay.
All right, let's thank the speaker one last time. Our is now on break. Optimistically, we will reconvene at 11, so check back in at 11. We will see you then.
Okay, I'll assume it is.
We've gotten a 1 second from the AV guy.
Okay.
You can vamp if you want. We don't have to be silent for a second.
All right. Yes, this is going to be a chat about Train, which is a kind of musical DSL and live coding environment that I've made kind of over the last year. Ooh, you can see that, but let's try and sort this out 1 second. Displays. How do I mirror this? Yes. Yes.
So you see that says NSN
Oh,
Illustrator?
yes.
Click that. I'm going to mirror it for the display.
Amazing. Okay, thank you. Okay, we can start now. Yes, so this is going to be about Train, which is a kind of live coding DSL written in this kind of Lispy language called Janet. So yes, it's a sort of music playground as well. So you can play around with different sounds and sound designs. And it has module visualization, so you can see what's kind of happening when you run your codes, and twistable knobs, so you can easily kind of tweak the sound.
One more tick, please.
I don't know if we can hear this. Let's see if the sound. Yeah.
So which one are we using?
It should be this one, this HDMI.
And what's the volume set at right now?
Full, it should be.
Well, that's not full. That's grayed out. So there
Yes.
is no audio registered to that device. So sorry to interrupt the talk with this. So that's not going to work.
We could play it through the speakers. I think they're quite loud.
They are quite loud. The trouble is about a third of our audience is across the internet. We could point the mic at it. Let's do that.
Let's do that. Okay. Let's see if this works for you.
You're muted now.
So, I think you can hear that. Hopefully, yes? Okay. So, we can kind of see that this is a sort of sample which we've loaded. This is its waveform. You can twist these knobs to kind of adjust the gain. Yeah, so if we maybe want to get rid of something, we can just delete this reverb. oh no, I've got something connected to that. Let's maybe just delete this delay. And then we don't have a delay anymore. I don't know if you can hear that. Let's add it back in. And then adjust its feedback. So yeah, that's kind of the idea. Thank you. Yep, so it's written in this kind of Lisp-like language called Janet. It's a really nice one. It's about 1 megabyte, and you can embed it in a browser by compiling it to WASM. There were some graphics playgrounds made by this guy called Ian Henry, and he also wrote them in Janet as well. And I really loved them. I'll show you one of them now, because I think they're really nice. So this is Toodle.studio. I'll again make this bigger. But on the left here, you've got some kind of Janet code, and it's controlling turtle graphics. So if you remember those, I learnt some of it in school. And I really loved all of these. There's some good examples here as well. And so I decided to basically take the best bits of Sonic Pi, which I liked, and some of this, and just mash them together. So when we're kind of writing train programs, you can think about them in kind of 2 halves. On the left half here, I've got this kind of syntax for creating modules. So these are things which create sound. So I've got a synthesizer called Hello Synth here, and that's plugged into a reverb, and then that's plugged into the kind of main output. And this chain thing kind of chains things together. So it takes the kind of output of this first form here and plugs it into the input of this one, and then the output of this into the input of this. It's just like an effects chain, like that. So that's one half of the language. And then the second half of the language is, well, okay, we've got this kind of, these modules sitting somewhere, and they're all plugged into each other. But how do we actually make music on them? And so you can do that from these things called live loops, which, again, I've just stolen from Sonic Pi. And they're like regular kind of while true loops, but they run in their own thread. And they have some kind of internal clock. So when you're calling this play function here, which plays a note on a synthesizer on this Hello Synth that we've created over here, it's going to play that at the live loop's own internal clock time, basically. It's got this local time variable. And when you call sleep, that just advances the time variable by that amount. Is this all making sense? Great, OK. So yes, we kind of saw earlier that modules have to have a name. And that's because we want to send them events later. So kind of parameter changes or play events. And after you've created a module by just wrapping its definition in some parentheses, you then can refer to it by its name. So if you want to do extra wiring on that later, you can just use its name. OK. You can kind of wire these together to create different sounds. We saw a bit of that earlier. And wrong wiring, where the compiler can kind of work it out. If it knows it's definitely wrong, like there's something which exists and you plugged it into the wrong thing, it will shout at you. Let's have a look at that. So here's another example. Here I've created this LFO. It's a low-frequency oscillator. It's just an oscillator which is kind of oscillating at like generally below audible frequency. And then here I've got this actual audible range oscillator called Oscar. It's plugged into an oscilloscope called Oscilloscope, and then that's all plugged into the output. And so if I run this, that's very loud. I'll turn it down. You can kind of see, yeah, I've got an oscillator. I can change its frequency like that, which is very fun. And then this LFO is just sitting there. It's not connected to anything. So I can use this other kind of wiring primitive here called wire. And this will wire the output of modulator, so it's this thing, this LFO, into Oscar's frequency. So Oscar's got a frequency knob here. And I can instead of doing this manually, I can just get the code to do it for me. So I'll turn this up again. And then fiddle about with these. And you can kind of see, maybe let's change the, yeah, so we're kind of doing some frequency modulation stuff there. So this LFO is kind of just modulating the frequency on that oscillator. And if we instead like change one of these names to the wrong thing, this is going to say, there's no thing called modulato, what are you talking about? And it will say, that's wrong. And it won't let you run that code. And that's kind of to stop these sorts of errors happening during performance. I've definitely had situations where I've kind of not heard any sound and I'm kind of struggling to work out what's wrong. So that's designed to help make those better. Okay, so we've now learnt about some wiring stuff, and if we want to actually play notes on things, like I said before, you have to do it from a live loop. And yeah, they're like while true loops basically, but they run in their own thread. They have to have a name as well, so this one's called player, or like drum player. And yeah, you can have kind of as many of them as you want, and they should all run kind of concurrently. So this live loop will play the note C1, which is a very low C note on a piano, and it will play that on the Hello Synth kind of module with a duration of 1 beat. So the kind of unit of time in train is the beat. And this will sleep for 1 beat, and then it will play a C2, an octave higher, and then it will sleep for a beat again, and then it will go back to the starts and do that forever. And if you change anything inside of a live loop, the next time it runs, it will play the new code. Yeah. Okay. How are we doing for time? We're great. Okay, thank you. So we can also change, instead of playing things, you can also change parameters, so the module knobs at specific times from a live loop. So let's see an example of that. If we run this, sorry, that's very loud again. You can kind of see, we've got this oscillator, and it's plugged into a scope, and it's plugged into the output. And I've got a live loop here, which is periodically changing the frequency, Oscar's frequency, this thing here, from 500 to 100. Yeah, so that's what it does. You can change these things, so let's change that to a 200. And then, oops. Yeah, it's live coding, you can do it all live. Okay, I hope this is all making sense. Oh, there were some other things as well, actually. Instead of thank you. You've got a few other options here. So this one's called lin. So that will linearly approach the value you want. Except this isn't working for some reason. Let's have a look at that. This could be a bug. Oh, there we go. So we're kind of linearly going between one or the other, which sounds strange. Okay, thank you. Okay, you've got some regular harmonic stuff like chords and scales, and in train they're generator functions. So you ask a kind of language to give you a scale in a particular key and type, like a C major scale, and then it will return you a function, and then the function, you can kind of use it as an index. So if you want the first note of the scale, you just call the function with 0, and so on. So we can have a look at that. So this one's just thank you, sorry. So this one's kind of just using this scale generator here, which is a C major scale, starting on a C4, which is like the middle notes on the piano, I think. And you can change it to a minor scale if you want, which is just a natural minor or a melodic minor. Or what else can you use? You can use a chords generator, which I've also defined here. And you can index like backwards into them, of course. So if I do
this isn't Lisp. There we go. So it just goes the other way. Yeah, that's the idea. That's harmony. Thank you, May. Patterns. So writing all of these plays and sleeps can be like kind of verbose. So you can use patterns, which are like a kind of rubbish version of the ones you have in Tidal and Strudel, but they work in a kind of similar way. So let's have a look. So here I've created a drum kit, which has some Roland 909 kind of hits in, and they're plugged into a scope. And then I've got some live loops which play notes on that drum kit. So you've got this thing, and this is playing the 0th and the 5th sample of the drum kit. So it's the bass drum and the snare, kind of alternately. These like subdivides in time. So if you stick those in a tuple, and then that kind of divides in time. So yeah, the way you can think about this, you can create patterns with this P thing here, and then you give it a tuple of things you want to play, and then the last argument is the time you want them to play over, and it will return you a array of tuples like this. So it's a note and a duration, and you can use those to sequence with. Yeah, that's the basic idea. You can instead, there's like Euclidean stuff in here as well, so you can replace this with, I think it's called Euclid. 3, to do the 1, 3, 8. So this means I want to play like this Euclidean rhythm, which is kind of trying to space out some hits over a number of sort of beats. And this is going to play the 0th notes 3 times over 8 beats. You've got the hi-hat playing as well, but let's get rid of that. So that's... Sorry? An E. Oh yes, you are. Yes, it's yes. Yes, it's like a capital U. Yeah. There is an internal Euclid with the correct spelling. Yeah. Thank you. You've got some random functions as well in there. So pick 1, 2, or 3. It picks between its arguments. Rep repeats the first thing by the second thing's number of times. So rep 1, 5 gives you 5 ones. And so if you want to choose this kind of custom distribution of numbers to pick randomly from, you can do it like this. You can repeat 1 5 times and expand it into the arguments. So that's what the semicolon operator does. Yeah, there's probably a nicer way of doing this, but it seems to work well enough for me. There's seeding randomness as well, so you can set the seed of a random number generator if you want to perhaps experiment with random generation but have things kind of repeat in this kind of predictable way. Or if you send a track to another person, they can hopefully hear the same thing as you as well. Syncing live loops. So you can have as many live loops as you want, and they kind of all exist in this virtual time. But if you start one and you create another one, they don't necessarily have to kind of start at the same time or play over the same time. But if you want them to, the way you can do that is with this till measure length. And till measure length, if you call it, say here from loop A, this is it's kind of virtual time, it will return to you the length of time until the start of the next measure of that length. So if we have a 64 bar measure, so this whole thing, loop A starts here, and the first thing it does is it calls sleep until the next 64 bar measure, and it will sleep till here. And then it knows it will always kind of evaluate over a 64 bar beat, sorry, I should have said beat, kind of length. And so by doing that, you can kind of keep these things in time. Yeah. I think, yes, I'll leave some time for some questions and stuff. Yes, you can have a look at the, you can play around with it here at lisp.train.studio. The code is all here under AGPL. And yeah, there's some example tracks here if you want to have a play around as well. And there's also some useful links here. So this Janet guide is a really good Janet book. It's all free, so you can learn Janet that way. And then the Sonic Pi website is kind of what the kind of the language is kind of based on. So you can have a look at that. Yes, I think that's it. Thank you.
We have time for a couple of quick questions.
Thanks for the talk. I wanted to ask about your motivation for creating this tool and whether how do you see it as different from other live coding languages, I guess?
Yes, it was born out of the desire to have, I guess, more control over the sound that I was making. You can kind of create your own synths in Sonic Pi and other languages as well, but it tends to be not the most simple process. And I kind of wanted something you could instantly kind of tweak around with the sound a bit more. So it was kind of that. And also being on the web, it's nice to be able to share links with people. That doesn't exist yet, but yes, that's kind of the main motivating things. Yeah.
Hi, that was really cool. I was wondering, so you've presented us a Lisp thing. I've seen Sonic Pi before, but this is Lisp. Do you have macros in this language?
You do. You can define your own and kind of play with the language a bit. It's all completely up to you. So some of the things you saw were implemented as macros. Yes, don't look at how I wrote them. They're all horrible.
As most macros end up being.
Thank you.
So we'll take any future questions offline. Let's thank the speaker again. Time to ask whatever questions it takes Alex to set up.
Yes, I do, yes. for lunch? Right, Firefox. Oh. Maybe that's good enough. We should just go. Okay. Right, so hello. Yeah, I'm Alex. I'm from a very small non-profit based in the UK called Then Try This, where I am funded by UKRI to investigate algorithmic patterns as part of a fellowship. I'm here to talk about live coding. I've got that wrong. It should say from Conical to live coding. So I'm looking for ways to be inspired by Conical to develop my live coding practice. I don't know why I got that around the wrong way. I think it's okay on my paper. So the software environment for this talk is Tidal Cycles, written in Haskell, and Strudel, which is a port of Tidal to JavaScript. So that runs in a web browser. I kind of think of them as the same project. I work on the representations in Haskell and then port them to Strudel with all the kind of libraries that JavaScript affords. It's free open source. Lots of people use them around the world. I don't know how many. But it's for performing with generally musical patterns as pure functions of time. And I'll sort of refer to these two systems interchangeably. I might try and go full screen there. So the aim of this is to design new support for stepwise pattern making within cyclic talas. I'll try and explain that a little bit later. Inspired by South Indian music, specifically this practice called Conical, which is a very advanced practice developed since around the year 200. Involves non-lexical syllables, i.e. Kind of nonsense syllables related to strokes of the mridangam drum. So has some relationship with sort of speaking drum strokes, where the syllables represent particular articulations of this two-headed drum. So these syllables, here's some of the kind of traditional groups of syllables. These groups of syllables are known as solkatu. And they are identified by the number of syllables in them in this list. So Tadaginatom has 5, Tadaginatom with gaps has 7. These aren't all of them, this is just like a selection. And they kind of relate to the mridangam drum. There isn't a one-to-one mapping, but it sounds something like this. Okay, so that's solkatu. Here's some actual Conical musicians. That's BC Manjanith on the right, who I've been learning Conical from, or Conical rhythms recently. So yeah, let's have a listen. That's a shame. Yeah, maybe I need to type that as well. So towards the end there, you maybe heard these repeated phrases getting shorter and shorter. That was a Tirmana structure, I believe. And you also noticed they were clapping a rhythmic cycle, quite a complex one. I'm not sure which one it was. But repeating it over and over again, I think at some point in this video they reverse it. But it's a very kind of geometric practice in these kind of rhythms grow and shrink over time, but there's always this underlying repetitive tala with the clapping underneath. So clapping the tala. In this presentation, I'll demonstrate the Rapaka tala, which the kind of default one is just clap, clap, wave, and a wave is usually you actually just turn your hand over. So that's like a 3-step tala, and the other one is Mishra Chapu tala, which is a 7-beat tala, but you go 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. So that's kind of the practice as far as I understand it, repeating these geometric chord structures, reciting them while clapping. So this is one example in the Misra Chapu tala. Maybe you can see I've just got the numbers 1 to 7 here. Each step is like 1.5 beats, then 1 beat, then half a beat, and then half, 1, and 1.5, which you can also see in this code. So I've just made this function in Strudel and Tidal called expand, or step expand, where you can put in these sort of step durations, and then it will repeat them over time. Underneath it says wave, wave, clap, clap. That's the tala. So this would be wave, 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 clap, clap. So it's something like 1, 2, 3, 4, 5. Yeah, I'm not sure if I'm going to be able to do this. So try again. 1, 2, 3, 4, 5. 1, 2, 3, 4. Yeah. Let's try just with this. I'm going to have to. Yeah, this is going to be super annoying. So you can kind of hear that it goes out of the tala, then back in again, just because if you add 3 times 7, then that obviously divides into 7. So with the sol katu, it would be something like ta, ki, ta, ka, de, mi, 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 ta. There, managed it. So, I think this is really nice. Like, it's very algorithmic, but it's also has a whole culture around it. So it's super interesting as someone developing live coding languages to be inspired by this kind of thing, and also get the sense that this is something you can do yourself. You don't need a computer. So when we get the solar flares that wipe out all our computers, we can still carry on. And so I've just generally got the, trying to take the approach where I'm not going to ask my computer to do algorithms anymore if I can't do them myself. Right, so here's another one. So here we were kind of expanding and contracting time. This is a Yati structure where you either add or subtract beats. So this is in Rapaka tala, so it's clap, clap, wave. Maybe we could try and do this together because it's quite nice to try and feel the beats move around while clapping. So if we do whack, clap, wave, clap, clap. Maybe slightly slower, actually, thinking about it. So rap, clap, wave, clap, clap. So 1, 1, 2, yeah. 1, 1, 2, 1. Hang on, I'm going to have to listen to it first. I'm a bit nervous. And also plug it in here. 2, yeah, okay. Let's try again. 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 1. Yeah. So, tack, tack, tack. Tataka, takita, takadimi, tatagina, tom tadim, gina, tom tadim. Tom tadim, gina, tom tadim, gina, tom tadim, gina, tom tadim. Didn't quite manage it, never mind. It's much easier to do it when you're on your own when you're on stage, I find. So that's kind of, and here I've just made a taper function. So I'm tapering, adding, and then tapering by 1 to make it shrink again. So it's quite fun to try and come out with these structures that have this kind of geometrical, rhythmic approach, while still fitting an underlying kind of cyclic structure inspired by this kind of thing. So onto implementations. So tidal and strudel kind of very cycle-based, which is quite unusual for music technology. Stuff. So when you do any kind of operation, it tends to be relative to the metrical cycle rather than individual steps. So there's no real way of adding together 2 cycles of different length. You don't add beats together. You start with a cycle and then divide the cycle up. So if you try and concatenate 2 patterns, then this sort of thing will happen. So you can hear half of the cycle has got 3 things in, and the other half has got 4 things in, because that's what you end up with, begin with here. But now I've made this step cat function, which actually does take the number of steps into account, and so it will then sound like this. So that seems really simple, like just being able to add beats together, but actually you couldn't do that without kind of adding some extra maths in to shrink and grow them by the right amount, which is a bit odd. But the reason for that is that the underlying implementation is inspired by FRP. So a pattern is just a function from time, a time span to events active during that time. Each event has the time span within that query where it's active. Might be a fragment, so in that case, you have to have the whole event as well as the fragment that's active. And a time span is just a begin and end time, which is a rational number. So what you end up with is a representation, whereas a pattern is not a data structure, it's a function, it's completely opaque. You don't know how many steps are in there, and it might change over time, so you can't actually take... There's no way of finding out what's in there without querying it, and then it's too late. Because when you're manipulating a pattern, you're not actually dealing with the data within it, you're actually making a new function which calls the old function. So, and you don't actually query it until it's time to turn it into sound. I came up with quite a complicated way of fixing this by splitting the pattern into a type class with 2 instances, one functional and one based on the data structure, which was really fun. Took months sort of working through this, but then realized it was just too complicated. And in the end, I just went back to the original representation and added some metadata, which just says what the tactus of the pattern is, where the tactus is the clapping rate. So if you have a group of people listening to music, ask them to clap together. The idea is that the tactus is what they choose to clap. So it's not the number of beats, because it might be quite a complex structure, but it's kind of this perceptual idea of the tactus. What is that kind of feel? Which is ambiguous, but that's part of the joy of the tactus, I think. So I did tactus, and also something, the pure value, just for like efficiency. I won't go into that. There's some more details in the paper if you're interested. How am I doing for time, May?
Well, we did start a bit late, and we have to keep you opening Jack Audio Connection Toolkit. So I'll say, 3 or 4 more minutes.
Okay, I'll go super quickly. I'll just explain the joins. So often you'll end up combining 2 patterns by doing a functor map, and then the values doing something with that value with another pattern, and then you end up with a pattern of patterns, and then you have to join them somehow into a pattern again. So the normal join will just do this. Hey. So here we've got 2 patterns, which end up being a pattern of patterns, and then the join will just line them up, and then you can add together the values. But then you can also do an inner join, so just use the structure of the inner pattern. Or the outer join to use the structure of the outer pattern. Or a squeeze join to squeeze the structure of the inner pattern into the outer one. But now I know the tactus of the patterns, I can do something like a polymetric join, where the sort of steps are matched up over time. That's a bit fiddly, that syntax, but in Tidal and Strudel, patterns are numbers, so you don't have to do all that functor map stuff directly. You do have to wire up your jack. And then you can choose the different joins like this. Yeah, there's more details in the paper about how to choose what the tactus is, which you can do in the mini notation. There's another function called tour, which is where you can place a pattern at different points within a list of patterns. I was also thinking about demoing how to put this into practice, but luckily there's a whole concert on that later, and I'll be performing as part of that. So I'll just finish then by thinking about the kind of wider context of Konakol. So this quote from T.M. Krishna: "In all Indian musical traditions, learning, rationalization, and sharing are part of the internal process within and between artists. The magnificence of this non-scribal technique is the acceptance of diversity and the possibility of continuous musical change. At no point is the music etched in stone, trapped in time, a stone tablet of commandments." I think this is a really beautiful idea, and I think there's something really special about oral traditions which aren't so focused around notation. And it's quite a strange sort of inspiration for something like live coding, which is so notational, but it's also very kind of ephemeral. If code is only made to be changed and deleted at the end of a performance, then it is becoming more like speech in a way. And I think it's nice to think about how we can move beyond this sort of this idea of algorithmic music being tied to the score or software engineering or something like that, thinking of something that's much more about exploring ideas live and with our friends for the moment. So yeah, thank you for your attention.
So we can take questions while we load up the video. Our next talk is going to be pre-recorded because the speaker is undergoing a medical procedure.
Any questions? No.
So I loved how the various joints sounded, but I wasn't quite sure how they worked. So in an inner join, you have this kind of pattern, and then you have you've sort of joined it with another pattern, and it's moving through both at the same time in a way I'm not sure I quite understand. Is it okay?
Yeah. So
hello everyone. Firstly, we apologize, but it was not possible for us to be present at Milano. And I would like to thank the organizer, in special Mae. Firstly, we apologize, but it was not possible for us to be present at Milano. And I would like to thank the organizer, in special Mae, for allowing us to present our paper via this video. We are Karim Haddad, the composer, Gonzalo Romero Garcia, and myself, Carlos Sagon. And we work at IRCAM. Hello, everyone. Hello, everyone. Firstly, we apologize but it was not possible for us to be present at Milano. And I would like to thank the organizer, in special Mae, for allowing us to present our paper via this video. We are Karim Haddad, the composer, Gonzalo Romero Garcia, and myself, Carlos Sagon. And we work at IRCAM at the musical representation team on the Open Music project. So the paper we are presenting today is a bit particular because it focuses on a sequencer in Open Music called the Maquette, which was actually introduced at this conference many years ago. So the obvious question is why we are talking about something that is over 20 years old, or more than 20 years old. The main reason is that the maquette has always been discussed from the user's perspective and never from a computer science standpoint. In other words, we have never really given a formal definition that explains the underlying semantic of this maquette. So today, I will try to explain why it is important to go beyond just a discursive explanation of the semantic, and I will also discuss the impact that we are aiming to have on Composer. So here is the plan for the talk. Firstly, I will start by showing you some examples of what a maquette is. Then I will explain why it's natural to understand this sequencer from a monad perspective. And finally, I will try to answer the question, it is really important for a composer to understand what a monad is? So let me begin by introducing Open Music. So Open Music is a functional programming languages designed by computer music composition, developed in Lisp at IRCAM over 30 years ago. So the main idea behind Open Music is to enable the composer to create functions that generate and transfer musical material. For instance, here we have a function that is called transp definition. This function takes two arguments. There is a graphical definition of the function that take two arguments. The first one is a list of MIDI numbers, and the second one, a number of semitones. That's called tones. And the answer of the function is a list of MIDI numbers transposed by this number of tones. This is a very, very, very simple function. This function, of course, can be used within the definition of other function. For instance, here, in this example, when we evaluate the function with these two arguments, here we have the function, and when we evaluate it with these two arguments, the result is a list of pitches that correspond to this chord that we. Hello, everyone. Firstly, we apologize, but it was not possible for us to be present at Milano. And I would like to thank the organizer, in special Mae, for allowing us to present our paper via this video. We are Karim Haddad, the composer, Gonzalo Romero Garcia, and myself, Carlos Sagon. And we work at IRCAM at the musical representation team on the Open Music project. So the paper we are presenting today is a bit particular because it focuses on a sequencer in Open Music called the Maquette, which was actually introduced at this conference many years ago. So the obvious question is why we are talking about something that is over 20 years old, or more than 20 years old. The main reason is that the Maquette has always been discussed from the user's perspective and never from a computer science standpoint. In other words, we have never really given a formal definition that explains the underlying semantic of this maquette. So today, I will try to explain why it is important to go beyond just a discursive explanation of the semantic, and I will also discuss the impact that we are aiming to have on Composer. So here is the plan for the talk. Firstly, I will start by showing you some examples of what a maquette is. Then I will explain why it's natural to understand this sequencer from a monad perspective. And finally, I will try to answer the question, it is really important for a composer to understand what a monad is? So let me begin by introducing Open Music. So Open Music is a functional programming languages designed by computer music composition, developed in Lisp at IRCAM over 30 years ago. So the main idea behind Open Music is to enable the composer to create functions that generate and transfer musical material. For instance, here we have a function that is called transp definition. This function takes two arguments. There is a graphical definition of the function that take two arguments. The first one is a list of MIDI numbers, and the second one, a number of semitones. That's called tones. And the answer of the function is a list of MIDI numbers transposed by this number of tones. This is a very, very, very simple function. This function, of course, can be used within the definition of other function. For instance, here, in this example, when we evaluate the function with these two arguments, here we have the function, and when we evaluate it with these two arguments, the result is a list of pitches that correspond to this chord that we can see here and that we can hear also. Okay, so each time that we evaluate this function, we get a result with a list of pitches that correspond to this chord. Now, what is a maquette? A maquette is a sequencer where we set function rather than musical material. The main idea of the maquette is to place function within a specific context. In other words, a maquette acts as a context where we can position functions to abstract their evaluation and their functional composition. For example, let's take our function and place into this maquette 3 times. So I take my function here, and I want to put 1, 2, and 3 times in this maquette. And then when we eval and play the maquette, we can see here 3 times the core produced, but the evaluation of this function. But of course, because this is a sequencer, the idea is that I can change the position of each core that is given by the horizontal position of these boxes. And then we can play again. In this example, we are only considering the horizontal position of each box. But there are actually many other parameters that we might want to use. For instance, if I put my function in this other maquette and evaluate it, I get this score. But if I change the color of the sequencer, I take another color and I put this one, for instance, and evaluate again, I get a different color. What's happening is that it is the same color, but transposed by a number of semitones based on how much red is the color on the maquette. So if I put a big quantity of red in this new color, so at the evaluation, my curve is more and more transposed. Here is a more intuitive example where the transposition of the curves depend on the vertical position. When I move the boxes up and down, so when we move the boxes up and down, there is changes in a way that is more natural from a notation perspective. Finally, here is an example where 2 programs are functionally composed. The composition is denoted by this link, which indicates that before evaluating the lower function, we need to evaluate the upper one. And in this particular example, no matter where I set the onset of this box, the lower one, after the evaluation, the lower one adjusts its position to follow immediately after the upper one. For instance, if I move the box here, after the evaluation, the second box meets at the end the first one. It happens because before evaluating the lower box, it takes the onset and the duration of the upper function as input here, and additionally, to calculate the core, the lower function also adjusts its onset. All right, so how do these examples work? Let me take a look at this maquette, which is a bit simpler than the other one. The trick here is that we have added 2 extra variables to the input and the output of the function. These two extra variables give us the characteristic associated with the function called in the maquette. Visually, this addition is represented by this box, where we can get information like the offset, the duration of the box, the color of the maquette, and many other different parameters. So in this example, we take the vertical position of the box and we use this information to transpose our code. For this reason, the three calls of the same function will be produce different results. Okay, now it is time to talk about monads. When we try to give a semantic to the expansion of output types in our function, the concept of monadic function naturally comes into play. When open music function is placed into a maquette, it becomes a monadic function because we have expanded the function's type. In our paper, we use the state monad, where for simplicity, we only consider the function's onset and duration as information. In fact, the state of these monadic functions can be defined by the composer without altering the semantic of the evaluation. In this article, in this paper, we propose an initial formalization of the semantics of maquettes using the state monad. However, there is still work to be done when it comes to the hierarchical structure of maquettes. It is since we have elevated the maquette to the level of a function, nothing should stop us for placing maquette inside another maquette. As you can see in this example, I can get a new maquette and put into this maquette and put into this maquette other maquettes, and the result after evaluation is the combination of two maquettes that we can evaluate and play. Okay, before wrapping up, I would like to take a few minutes to address what I think is the most important question of this paper. The question is, does a composer gain anything for knowing what a monad is? In fact, the maquette in open music was proposed by two composers, Tristan Murail and Joshua Finberg, and based on their ideas, we implemented the sequencer in open music. So another way to rephrase the question will be to ask whether it will be useful for these two composers to know that their intuition align with a concept from category theory called a monad. Personally, I am curious to know the opinion of these composers if one day they read this paper. But now the answer that I would like to give to the question, does a composer gain anything for knowing what a monad is of course, yes. My answer, of course, is based on two musical issues that I believe are well taken in account by the monadic approach. The first one is the concept of timing of the musical material. As we said at the beginning, functional programming is useful to modelize the construction of musical material, but it is not the case to modelize the set in time this musical material. Or in any case, these two things don't follow the same logic. And I think that the separation of these two procedures can be well taken in account by the concept of the monad. The second issue concerns the musical form, and in particular the relationship between different parts of a piece. The musical form is a very abstract notion. Sometimes we talk more about the elaboration of the form than the discovery. And it implies that the relation between parts are more than a casual or a temporal relation. We need an arbitrary notion of what the composition of the part is, and for me, this is the exact definition of a monad. As we put in the paper, the monad is the abstraction of the functional composition. It is important for me to show that all this abstract theory gives concrete results in terms of music. Let me show for this a piece called First Attempt Escape from Silence, is the section Tunnels. And this part of the opera is composed by the composer Karim Haddad. And we can see here a sketch, a maquette of the piece. And then we can see a first proposition of the structure modelized in the maquette in Open Music by the composer. And at the end, the final result after some computation of this structure. All this hierarchical structure and functional composition is hidden when we listen the piece. I invite you to listen an excerpt of the piece.
So catastrophic. No one remembers it anymore. Does anything not have a flaw?
It's another die. A parent, a child, another suicide.
I want to offer my sympathy. I know they won't understand me. It's said they are afraid of violence.
heard? Is it said?
To conclude, I would like to add that functional formalization based on the principles of abstraction and application is for us, above all, a creative strategy. The idea is that a computer experimentation pushes the composer to modify the model more than the result, and this is for us a truly artistic gesture. Thank you.
We will not be able to take questions as the authors are not online. We have one last talk in the session. I reordered it without telling you all because I was hoping in the 20 minutes it took us to watch that we would get audio for your laptop. Let's see if we do. We'll try it. I should also note that, as with everything in this conference, that talk will be available online with synchronized audio. So if you need to rewatch it, it is available.
Okay, duplicate. No, you want to duplicate it. Oh, you want me to place them on? Sure, sure. Actually, yeah, sure. Yeah, one second. Good? Want to keep going? I'll leave it. Oh, okay. That doesn't sound like good. All right, sound. This guy, okay, I'm on HDMI to USB, but the volume is grayed out again, like before.
The Macs don't have, so far the Macs have not recognized an audio channel on that device at all.
Oh, wait, this guy doesn't, hold on. This guy doesn't obey the rules of the sound menu. That's my fault.
Yeah. One moment. Yeah, this is correct. I think so.
You see an audio device corresponding to anything device.
Yeah, it's not working for me. I'm not a great audio engineer. I couldn't really tell you how to fix it. Like this is what I'm looking at. And I selected the device HDMI to USB. What's that? Oh. I am playing sound, yeah. Allegedly. think so too. Okay, that's fine. There we go. All right. Welcome to my demo. This is a demo about my music composition language, tone art. So welcome to my demo. Tone art is a language about a language for composing, and it's all about you get a score-like context in which you write an extensible music syntax. So you can think about it as abstract syntax for a traditional music score. And operationally, it feels sort of like a stack-based language, but instead of pushing values onto a stack, you're writing notations onto a music score. And instead of running operators on a stack, you're running rewrites over the score or parts of the score. So you specify score structure, and then you write notations in that structure. And score structure is specified using coordinates. Tone art programs usually have two coordinates. There's voice, which corresponds roughly to the vertical dimension of the score paper, and so which staff the notation will go on. And then there is interval, which corresponds to time, the time dimension, the horizontal dimension of the score. So a beat interval, what beats the notation goes in. To specify coordinates, we use the at form. And this is where we'll start coding, and I will zoom in. Is that big enough? Okay, good. So we use the at form to specify coordinates. And the first subform of the at form is a list of coordinate syntaxes. So you see we've got, as I said, our voice coordinate, we'll say soprano for now. And we've got our interval coordinate, and that is a range, so beat 0 to 4. Okay, and close that. And in here, anything that we write in here, I put the dot, 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 will be inside those coordinates. So in the soprano from beat 0 to 4. So we'll introduce our first notation, and it's going to look like this. And that is our syntax for traditional, iconic notes that you see on scores with the note heads and the beams. So we can try to evaluate this form, but it won't work, and that's because this is a Racket REPL, and this is a tone art program or form. And so tone art is a DSL that's embedded in Racket. But we need something a process that takes us from tone art to Racket. It's a compiler is what it really is. And I call that process realization. The reason I call it that is because you've got like tone art, which is like a notation, it's like kind of abstract, it's like an image, and then you take it to reality. Or actually, in the case of this implementation, you take it to Racket, which is the next best thing. So the form for that is called realize, and this is a form that's an interface between the DSL, which is tone art, and the host language, which is Racket. And so realize, the first subform, is a realizer syntax, and this is also user-defined and extensible. And so the first one we'll look at is the staff realizer, which is going to try and draw whatever tone art we give it on a score paper, or make something that looks like it. Yeah. So we can drop that in there, and you see the note C5 drawn onto a little staff. So a crucial thing about tone art is that you can take the same piece and realize it multiple ways. And so this realizer, we can use a different one. We'll use the play realizer this time. And the play realizer is going to try and play what you've written out of the computer. Now we can hit enter here, and it'll look like it's doing something, but then nothing will happen. So sad. The reason that is because realizers have input languages. And the staff realizer and the play realizer have different input languages. It's kind of like if you handed a person like the binary data for a WAV file and said, sing this. What are they going to do? And if you hand the play realizer notes, it says, well, what do I do with this? Play realizer only understands more computational like computer music-y notations, such as MIDI's tones or sound files. So what we need to do is we need to compile our note music into like tone or MIDI music or some mix of both. And the way we do that is through a process called rewriting. So ToneArt has these other forms called rewriters, and here's one now, note to tone, which are not notations. They do not go into the score context. They simply transform the score context, then go away. So if we run this note to tone, you'll hear it play a tone. I can only imagine how that came through the mic. And if you run note to MIDI, down here it's actually going to send the music over to, well, it's going to send it using MIDI, which is a protocol, and then I have Grand Org running over here, which is virtual organ software, and so it's listening for MIDI events, and it'll actually play back whatever we do on the organ. So that's fun. So we're about ready to start composing, but before we do, I want to introduce a few abbreviations just to make this easier. So equals is going to be the staff realizer from here on out. And you can see equal, and that's the staff realizer. And bang is going to be the play realizer. Same idea. And instead of writing these cumbersome at forms like this, I'm going to use voice at and then the voice. And I'm going to use I at and then the interval. And if I lost you at all, don't worry, I'm going to narrate it as I go through. Okay, so now on to some composing. So the first thing we probably want to do is give the soprano something more substantial than one note. So we'll try and design a melody. And there's a few ways to write sequences of notes like this. The one that we can do right now that we know is, I at 0, interval at 0, 2, D, interval at 2, 4, E, interval at 4, 6, F. And that's great and all, but it's really, really cumbersome and slow to type. So what I want to do instead for this demo is write down a sequence of notes, then a rhythm, and then use a rewriter to turn that into note music that, for example, the staff realizer can understand. So we're gonna define it. We'll make a little template for this and then fill it in. So define art just means make a binding that contains some tone art and that represents some tone art. And so we've got define art melody. This is going to be our melody. And in here, we'll have a sequence of notes, and some notes will go in there. And then we'll have a rhythm, and some durations will go in there. And then we'll have a rewriter that will apply the rhythm to the sequence to get note music. And so I'm just going to make up some notes that I imagine will make a good melody, and I hope it does, because if it doesn't, then it will sound bad in the end. So we're going to go up a little bit, and then down a little bit, and then up a surprising amount. That's not going to work. Put the right octaves in there. And then we'll stop on this G up here. Make sure those octaves. Yep. All 5. Very nice. And then the rhythm, we'll pick something 2, 1, 2, 1, 3, 3, 3. That should be fine. And that sums up to a total of 3, 6, 9, 12, 15. It's good to keep that in mind sometimes. Okay, so we've got our melody. Let's take a look at what it looks like. So we need to put it in a voice, so we're going to put it in the soprano, and then we'll give the soprano the melody. And there it is on the score paper using the staff realizer. And then we can, of course, play it as well. We can just go back to this, and we're going to use the play realizer, which is bang again. And we have to do note to MIDI so that the play realizer knows what it's doing. And then we can hear it in the organ. Turn that down a little. Lovely. And so that's our melody. Now we want to make a harmony. And we'll do the harmony in chords. So we'll use a very similar template to do exactly what we just did. Define art harmony. And we've got a sequence, but instead of notes, this time it's of chords. Okay? And then we've got a rhythm. And that's going to have durations, and of course apply rhythm at the end to make it into, well, it'll be chord music this time, but we'll deal with that later. Okay, so chords. We got to look at the score and figure out what chords we want. So this, we're going to do a C major. This is like the chords that you learn on guitar. It's that same, these very same chords. So a C major, then a major will work fine, and a D minor, followed by another C major, and then we can do a D major, because that's funner, and then oh, how about an F sharp? No, that's not as fun as I was hoping. A B major, yes, that'll be good. And finally, we'll end on a C major. And what's up?
It's okay.
Oh, okay. Anyway, yes. So we'll do the rhythm here. 2, 1, and 2 will be fine. And you know what? We'll suspend this into the D, and then how long is the D? 3. So another 2, and then the B major will be 3, and we could go right into the end of that a little, and then 2 there. Okay. So we'll see how this goes. Let's make sure they add up to the same. 3 plus 6, that's 9, plus 6, yeah, 15, great. So there's our harmony. So we'll see if May is right and it doesn't sound good. I think it will sound good. We will see.
I'm sorry.
So we'll start by showing it. The suspense is killing me. We're going to put it in just a random voice. And the harmony, and then we're going to show it, but as I said before, harmony is chord music. The staff realizer doesn't know how to show chords. We have to do a little bit of rewriting. I promise we'll play it soon. So we need to use a rewriter, and we'll use chord to notes. Makes sense, right? And now the problem is there's a lot of ways to turn chords into notes. So here's a C major chord, but this is also a C major chord, but so is this, okay? So, so we've got a special one. We call it /simple, which does the simplest possible thing. And that is to do this. Make these little, we affectionately call them snowman triads. Triads because there's 3 of them, and snowman because they look like little snowmen. So now we can finally play this. And note to MIDI here. And we'll see how it sounds. I want to turn this off. Make it a little quieter. So what do you think? You know, you can leave a comment or vote afterwards. I think it sounded great. So that's really nice. It's sounding really nice. Now I want to do something a little unconventional. We'll add a second melody, but that's not unconventional. That's normal. But what's unconventional is we're gonna do it out of a mathematical function. So you might be thinking, how are we going to do that exactly? And that's the fun of it. It's creative. But before we do that, we should probably have a way to draw functions because we want to actually visualize what we're doing with them. And so I'm going to provisionally introduce my debugging realizer. It's called the Draw Music Realizer, or DMR for short. And it's a debugging realizer. It will try to draw everything you give it, with mixed results. With mixed results. So here's what it looks like drawing a note. And that's whatever. It's not as good as the staff realizer, obviously. But it does useful things like it can actually draw the harmony, unlike the staff realizer. So that's kind of useful. So anyway, we'll do our function here, and here's a basic syntax. The first thing you think of: function x, sine x. That's our syntax for functions, and the draw music realizer just draws the text for it. Okay. Good try, buddy. So we want to start compiling it into something that makes sense and is more like a note. And I propose the first step as function to contour. And it has to have an x range here, so we'll do -pi to pi. And when we run this rewriter, we get, and I'm sorry for the red on red, again, the DMR is doing its best, but you get the curve for the function drawn onto the score. If you're anything like me, you see that, and you say, it needs to be wavier. So we can use our knowledge of the sine function and decrease the period, like like that, and now it's wavier. We can do some more, tricks to make it more interesting looking. That's definitely more interesting. So there we go. Let's call it a day there. So we've got our contour music, and now the final step is to turn it into notes. So we'll go ahead and start our template here, define our, and this is going to be melody 2. And we need to actually put it in time somewhere. So the interval from 0 to 15, the same length as everything else. Drop the contour in. And now at the end, we'll do something here. We'll do something here. And at the end, we'll end up running contour to notes, the rewriter contour to notes. So contour to notes needs some context, I would say. And one of those things is the lowest note that it's going to have and the highest note, so a note range, so that it can fill in between along the curve. So that's written as note range. And I'll look at the melody to pick a good note range. It starts kind of low and goes up a little, so we can probably go all the way from like G4 to C5, I reckon. Oh, sorry, G3 to C5. So we'll try that. Okay, so that's our note range. And then we need to give it a rhythm because it can't just do one continuous note the whole time. That's not a note. So we need to tell it like how often to sample from our contour. So we give it a rhythm, and I'm going to use uniform rhythm 1/4, which is just a shorthand for writing rhythm 1/4, 1/4, 1/4, 1/4 for 15 beats, which means we're going to, by my calculation, get about 60 notes out of this because there's 4 notes per beat and 15 beats, 60 notes. And then finally, we need to provide the harmony because it needs to select notes that sound good with the surrounding notes. And so it's actually going to use our chords as context. It's context sensitive to the harmony. So that is our second melody. And if we go back and go to our old composition here, we've got our melody and our harmony, and we can drop in our second harmony. And again, this is just a random voice name. Descant, if you're interested, it's a church music term for a counter melody, like a second melody. So we can draw this, and aha, there it is. There it is. It looks like it, right? It looks like it. It looks also a bit like a caterpillar or a snake. And we can give it a play. Let's give it a go. Note to MIDI, of course. And this is the part where you kind of cross your fingers, say a prayer, and just let it rip. So here we go. That was good there. That part at the end was pretty good. I like that. So yeah, that was pretty cool. I think it's pretty cool. And so just the last couple of things, I do want to show you something I pre-composed using the same techniques. How are we doing on time? All right, a couple of things. Something I pre-composed using the same techniques, but it's a little more substantial, and it also lets me show you the benefits of having an embedded DSL. So I'm going to use the Racket module system to require another composition. And we're going to do, so we'll do prefix in. Again, this is Racket module system. So this is going to append this little prefix before all the bindings that we pull in from the module. And the module is called toccata.racket. Okay. And so we'll pull in this composition. And there it is. And we can take a look. The cool thing about this is we've pulled in different parts of the composition. So we can take a look at just the melody. We need to put it in a voice for this for the staff to understand it. But we'll put it in the and we'll give the melody. And you can see this is the melody. It's actually quite low, so that's kind of interesting. Why is the melody so low? Ooh. So we'll find out. And this module provides a nice sample. Oh, I forgot the prefix. There it is. It provides a nice sample of how the composition could look. And so here it is. And it looks more complicated, but it's using the same exact techniques we just used. This top part is a sine wave being realized by the computer as notes. I changed the ranges a bit as it went along for expressive reasons. This melody is hand composed, and it's actually in the pedal part, so watch out for that. You'll see that it'll actually be on this keyboard down here. And that's sort of characteristic of this is a French toccata style, a French organ toccata. And then this bottom part is in the left hand, and it's the same exact thing. We've got chords, and then we turn them into notes. And I have a sort of chord to note simple addiction, so it's just the snowman triads again. But I hope you're okay with that. So we'll give it a play, and it's going to be default notes and note to MIDI. And let's see how it sounds. Let me make sure the organ is set up for this first. Okay, we'll add that later. This and this is coupled. This looks good. Yeah. Okay, we're ready. Right, so I hope you enjoyed that. I have one last short thing. I've always wanted to do this since I was a kid. I have to reveal to you that the script for this demo is also a tone art program. Okay, and I need to let you know that I think I've been doing an okay job realizing it, but I would like to tell you that there is actually a computer realizer for it as well, and so I just want to introduce my my co-presenter here, and here we go. And I'm also going to give him a little bit of counterpoint. All right.
Welcome to my tone art demo. Tone art is a language for composing music. The major idea behind the language is composition and is to provide context to extensible music notation.
Okay. So, yes, anyway, and so while the credits roll, I just wanted to acknowledge all the software I use, Dr. Racket and Racket, amazing. Chuck is the backend I was using to send MIDI and tones, Grand Org is over here. If you're interested in EDSLs and compiling them and multi-language and things, which should be of interest if you're here for this, because all of these languages have been interesting EDSLs, make sure you get to Michael Valentine's talk on Wednesday at 11:24. It'll be on that exact topic. Finally, I wanted to dedicate this demo to my two teachers, Matthias Verleisen and Peter Edwin Krasinski, and thank you all for coming. I look forward to seeing you around the conference.
Everyone can feel free to get lunch, but because what is time, we'll also take questions. I'll go ahead and start. It seems like you cheated there.
I did.
In the sense that pitch classes are not determined by what you're writing in the melody, but rather their function with respect to the harmony.
Pitch classes are not related to the melody. Yep, that's correct. Yes, exactly. I did. It's not cheating. It's a choice.
Okay.
Yeah.
If I wanted to differ from that, let's say that I wanted to insist that the first two C's in the melody are really the pitch C and not just whatever the analog of C is in the current harmonic moment. Can I do that?
Not with this realizer. But not with this rewriter. But you can write your own rewriter. This one is actually very simple as well. It does, like, for a major chord, it uses a major scale. For a minor chord, it uses a natural minor scale. If you were doing it for real, you would look at the surrounding chords and try to interpolate what accidentals you should use. So there's definitely more work to be done on that rewriter.
Okay, and I could write my own realizer that says, screw the surroundings, I'm post-serialist, I do what I say I do.
Oh yeah, absolutely, absolutely. That's what it's all about, baby. All right.
Cool, more questions? I think it's lunchtime.
Great.
See you guys all at the room. Yeah, down's good. So. Welcome back to the afternoon session of FARM. This will be the final regular session of FARM before our performance evening, which, as I've mentioned before and will mention again, is not here. It is in downtown Milan at the Auditorium San Fedele. It is near the Duomo. Take the M1 metro to the Duomo stop. You can walk there. It does take an hour. Our session here will conclude sometime soon after 3:30. Our last talk might run a little bit long, and that's okay. You will have about 3 to 4 hours to get, probably about 3 hours to get down to the venue and into the auditorium in time. During that time, we also encourage you to eat. So please bear in mind, a half hour down to the center of Milan, some food, 3 hours, plan. Also, I should note that our conference is limited to registration, but our concert is not. As with previous farm years, if you have a friend in town or someone that you've met on the street, please feel free to invite them to the concert. We are unlikely to fill the venue completely with all of the ICFP people who are here today. If, however, there is a conflict, we will prioritize seating people with badges over seating people without. I do not recall a farm, though Michael might, where this was a problem. Never a problem. Genuinely never a problem. Make us so popular that it's a problem. Please feel free to find me at any point to ask questions about this. Please feel free to get me on Discord or reach out to me over email. My email's sprayed about many websites. Some people will be leaving in the middle of this session, perhaps directly after their talks, in order to get to sound check. So if you are one of the later presenters, please do not be discouraged if you see like 5 people walk out of your room. They're just getting ready for tonight. And with that, I think that's all of our business concluded. So we're ready to welcome our first talk. Javier, take it away.
Hello, hello, sound checking. Make me a signal if I go too loud. Sometimes I speak very loud. Thank you. Well, thanks to Maya and Stephen for organizing this year's farm. It's really a pleasure to be here. Also, thanks for the reviewers, for the comments, and the program committee for selecting my work. It's really exciting to be here, and the talks so far have been amazing. So, well, what to expect from this demo? It will be half a presentation of the work in progress, which is related to my PhD research, and the other half, maybe not a half, but maybe less, will be showcasing what the RTG library. What?
I'm so sorry. I didn't plug your computer in. That's audio.
This is audio for you. Okay. Okay, so I will cover an overview of the project, the central ideas, and we see some examples. Full disclosure and, what was the other word? Anyway, the system still has many lackings, but I mean, there's a lot of exciting venues of development that I hope to convey to you today. Well, the research context. I have a background in mathematics from my undergraduate studies. Then I started my own practice as a music producer. And afterwards, this led me to pursue a degree in music technology, where I actually aborded technology from a critique point of view. Like, as a user, I was questioning about how does this power technology give me, how does this translate towards like critical comment on culture. And finally, I reach programming language from musical expression, which is my current line of research. Well, the inspiration for this project is mainly derived from two other projects. First, we have Tidal Cycles, which is a community-driven environment for creating algorithmic patterns for live coding. And also Chronomorph, which is an application that is designed to explore well-formed and perfectly balanced rhythms, which in a graphical user interface. Both projects have different affordances, scopes, and user interfaces, and both are capable of generating and transforming rhythmic patterns. Those are the interfaces. One is text-based, and the other one is completely graphical. So when we think about geometry, we usually think about the left side image. So you will see kind of figures in 2D or 3D representation. But I'm interested in how this representation or geometric properties translate into internal structures of the objects being manipulated, which in this case are rhythmic patterns. The design goals for the, well, I forgot to mention, the library is called RTG. We'll see what that stands for, but its design goals is to be a text-based UI and has a terse pattern manipulation as it is intended for live coding. Also, I want to implement smooth morphing between given patterns. And finally, evolving patterns using parameterized geometric properties. These are embedded into patterns, and then they will be used in the implementation background to do this kind of evolving and morphing. Right now, the development of RTG has been mainly focused on these first two elements, as I'm exploring like the feel of the interface for the purpose I want to give it. Okay, RTG stands for rhythm, time, and geometry. So talking about rhythm, it is about applying musical rhythm research to the generation of patterns. I also want to explore implementation strategies to deal with musical time, which I also found fascinating. And finally, which is the main element now that I'm exploring in the interface, is using pattern types with geometric properties accounted for in group operations defining an even geometry of patterns. Groups here are in the sense of algebraic groups. So, you know, this is the very basic structure that you get with sum, multiplication, even the basic isometric transformations of the plane and any kind of space. Okay, so what I want to use geometry for, it will be the framework for rhythmic pattern generation and manipulation towards a declarative, serendipitous, and expressive environment for music live coding. Actually, the serendipitous and expressive can become conflictive, because if you want to express an exact idea, that will be in conflict with the possibility of exploring like non-expected things. And I'm done talking about randomness. So far, I'm not interested in implementing randomness, but unexpected ways of combining patterns. And how I'm going to do that? Well, this will be developing a library based on type-level constraints that guarantee the musicality of the result in accordance to the geometric properties I just mentioned. And the current research scope has to do with Haskell type system, so I'm interested in using types to encode these properties and ensure the transformation and composition of patterns. In relation to rhythm geometry, the implementation of geometric properties as pattern structure, rhythmic grouping, balance, well-formedness. There's a bunch of research, mostly targeted toward analysis of music. So most music theory is about analyzing what already is, but I'm wondering, and my main target is to leverage this knowledge to the generative side, so we can create things on the fly. And also the syntax semantics of domain-specific languages for music. This is a broad scope as well, and I'm interested in like the ergonomics of language when you are writing. Well, I mentioned groups, and the Langen program is the conceptual framework that gives sense of groups to be thought as a manifestation of geometry. The legacy of Klein's Langen program is the conceptual understanding of groups as encoders of abstract geometric symmetry. And using groups opens the possibility of exploring the mathematical idea of symmetry transformation in the domain of music. This is really an open question for me and has been a leading in exploring sometimes difficult subject, because one central element of a group is to have an inverse of an element. So you will have a pattern and then you ask, well, what's the inverse of this pattern? And what will be an identity? Because that's a property. If you have an element and its inverse, its operation among themselves gives you identity, which might be silence, which might be a single event. I mean, you have to define it. And some definitions don't give you all group actions. Sometimes they are limited. So this exploration for me is like, okay, if I can give patterns group structure, then patterns can also have an inner geometry, like an inner geometric life inside themselves. If I can't, this what I'm seeing is that geometry in time has certain restrictions. And the interface, you can see some of this in the paper. First, I'm using the standard type class of subgroups. So that operator will be the subgroup operation. And the invert function is used to get the inverse of an element. So you will have, first you need an instance of subgroup, then monoid, and finally you have groups. Groups is just a monoid with the inverse property. And so far, I've been having a lot of fun working these things out, like developing this main interface, which is just a type class. So the last implementation, I set the constraint for the type to be a group. Before, I just wanted to just give me a way to operate the elements. Now I'm trying to force that for the type to actually be a group, for it to become a rhythmic type. So the interface is really simple, and internally what is being done is everything that can be converted to a rhythmic pattern will be a rhythmic type. That's the first to rhythm function. And rhythmic pattern is also the simplest representation of a pattern. I'm thinking about lists. So you will have binary elements represented either a silent moment or an onset moment when a musical event is triggered. Okay, so now I can go towards examples. I actually have, how much time I have left? I forgot to set my timer, and now it seems maybe 10 minutes? Okay. Okay. Well, I have these fallback videos because I never know. Sometimes my laptop is quite old. It has almost more than 10 years. But should work now. First, let me try these videos, and then I can do the live demonstration. I don't know if sound will be working. Wait. That should be going. I just showed you one kind of rhythmic pattern I have, which is time patterns, which are just basically ordered rational number lists. And these lists are eventually always translated to the representation I mentioned about rhythmic patterns. So we have zeros and ones representing both rests and onsets. Now, when having the logic separated by types allow me to define different operations using the same interface for different types of rhythmic patterns. And so far, everything is completely asynchronous. This is one of the biggest lacks of the system. I'm just trying now to test what kind of results I'm getting from the current definitions of the operation. Now, I also have an Euclidean type implementation, which is the common Euclidean rhythms. The third parameter accounts for rotation. And they can also be operated among themselves, with a definition completely different from what you get when you are dealing with regular time patterns. What you just heard, everything so far, is the result of a quick and dirty solution to getting sound out of the patterns, because before that, it was just number lists. I mean, before. So I'm just basically using the standard tidal cycles library and sending messages through OSC to SuperDirt in SuperCollider. So in this way, I'm getting sound, but buffering is still not implemented. So this is also fun so far. But what happens is the scheduler is deciding the exact timing of events. So now each event is like if two players don't know anything about each other and are completely isolated soundly, so they will play together for an audience who is actually listening. That's what's happening right now. So there's much work ahead for this part of the time implementation. Wait, there was something else I wanted to comment. Okay. Okay, the last video example. One of the main ideas is to, at least at this point in the design, is to avoid specifying a pattern explicitly. As far as this can go is when you call an Euclidean pattern, you give certain parameters, but it's not like referencing tidal cycles, like having a mini notation where syntax allow you to specify exactly how the cycle is divided. Now we assume patterns are given. So that 5B pattern and that Chico pattern are being combined through a different operation. They are being lifted toward the rhythmic pattern type and then combined. So the idea of the ampersand operator is that I can, so far there are only 2 different rhythmic pattern types. And as I said before, and this is one of the main points of where the group inspiration has led me, is to have them separated for them to have different operations. Now, when I use the ampersand, they are lifted towards being a rhythmic pattern and then combined using a standard predefined operation. So I can have expression like the last one when the priority is on the type operation. So for example, 5B will be mixed with the Chico rhythm first before being combined with the Euclidean rhythm. So I can decide if I'm going to combine operations using their own group operation or using the standard one. So then I can have combination of all the different types. And that's basically it. Thank you for listening. I will gladly take any questions. Thank you.
Fascinating work. I'm not sure if perhaps I'm the only one in the audience who's not aware of the background. But what is this Euclidean function that you speak of?
The Euclidean function is it's actually called the Euclidean algorithm. It's just an equivalent of the, it's a Bjorklund algorithm, which what it basically does is takes, like you have a set of ones and a set of zeros, and what it tries to do is to put them in a way that maximizes the evenness of the pattern. Like they are as well distributed as possible. I mean, if the two sets are coprime, then you won't have an even ordering. So you move from even ordering when you have coprime numbers.
No, you had a Euclidean function that took three numbers and produced a time pattern, correct?
Yeah. Yeah, the first number will be the number of events you will have in the pattern. Then the second number is the chromatic universe is called in the context of scales. In the context of rhythm will be like the even division of the bar. So you have an even division of the bar of 8 elements, and then you have 3 events, and they are put inside those 8 places, distributed as evenly as possible. The last parameter is just rotation of this pattern.
So another question that I have, and the last question, is you had 2 operations. There was an ampersand, and then there was the
diamond, let's call it.
Yeah, the diamond. The Lister pen, the monoid pen, right? So did you define those functions? I missed it.
No, they were not defined here. The definition is actually just suggested is on the demo paper, and they are referenced there to the code. Because right now the definition has I actually use the same Euclidean algorithm for pattern. The append function, the common one, is just appending, right? This diamond operator.
So the diamond operation is just appending to patterns? No, that's not.
No, what's happening, I tried that, and obviously it doesn't work that well because you get basically a big mesh of a pattern. But what I'm doing right now is I will take the 2 patterns, they may have different sizes, and I will take the smaller one and match the events, distributing the events as evenly as possible of one into the other.
Awesome, really good, thank you. I have a question. So in your abstract, you mentioned that the technique that you are developing produces or aims to produce interesting rhythmic patterns, which means that somehow you are tying that a rhythmic pattern that is interesting has to do with that Euclidean distribution. Can you elaborate why is that? Like, how do you understand an interesting pattern? Why is that interesting? Instead
Well,
of a not interesting pattern?
that is a direct reference to Toussaint's work, Gottfried Toussaint. He wrote this book, The Geometry of Musical Rhythm, which I drew a lot of inspiration from. And the question is, rhythm has no boundaries, and on actual performance, the time is not mechanical, it is felt, right? But within some of the rhythms that are performed, there are certain regularities, and these regularities appear as rhythmic structure when the patterns are analyzed. So this rhythmic structure, if you, like, what Euclidean rhythms does, they input constraints on the construction of rhythms such that they tend to be good. I mean, this good is obviously a matter of question, but what is argued by Toussaint is that good, at least, would mean that the pattern, for one reason or another, is used among different cultures in different places. This will be the thing. So it leads you to the question of universals in music, which is also a polemic question. But we know that certain things are like felt good, like the fifth. Few people will say that the fifth is not a good interval. It's apparently good because of some reason. But you start leaving these commonly agreed conventions, and then you start getting in a philosophical question. But that's the idea. The idea is to be able to call algorithms that generate patterns that are predisposed to be well-behaved, and then you start playing with them. So right now I can call the Euclidean algorithm or take patterns by name, and these patterns have cultural context. Yeah.
So that's all the time we have for questions.
Okay.
So happy to take any other questions offline. Let's thank the speaker again.
Thank you. Espera. Ups, no vaya a ser que esto explota. Okay, that should be fine. Yes. Okay, take it away. Thank you. Yes. Yes.
All right, hi. My name is Pierre. I'm currently studying design and computation as a master's program in the University of Arts Berlin, also the Technical University of Berlin. And I'm presenting my paper I wrote together with Christoph Weber and Sylvia Rothe. Both were my supervisors of my bachelor thesis I wrote last year. And this bachelor thesis we condensed down to the following paper of ours. The title of our paper is Diffusion-Based Sound Synthesis in Music Production. As a bit of a background why I started doing this, my bachelor's was in physics and computer science, quite technical, and besides my studies, I also did some music production, videography and photography. So I always wanted to combine those topics, and then I thought for a bachelor thesis this could be the perfect opportunity. And I thought music would be the best choice because there's this long history of influence from another. It's even dating back to Pythagoras. I really recommend this book if you want to check any more out on this history. But yeah, so generative AI has become more and more present the last 2 years, and we wanted to explore this field and usability in instruments and thus music production as a whole. For this, we built a digital instrument that uses latent diffusion to generate playable sounds. And around this, we came up with the following research question: are diffusion models suitable for use as a sound source in a music production process? More precisely, what we did, we explored the implementation of possible latent diffusion technologies and synthesizers, then analyzed the resulting digital instrument, and as well did an evaluation on the models in the context of music production. As a bit of motivation behind our project, I would like to take a quick peep into the current landscape of generative AI in music. So this came out, I think, a few months ago. It was after our product was finished. It's called Udio, and with it you are able to generate a whole music piece or a song from one single prompt. And I don't know, like the technique is really amazing behind it, but I feel like it takes away all the fun stuff in the artistic process, and there's not any decision making or creativity behind of it. And that's what we wanted to avoid firsthand. So our approach is that we are more for a hands-down approach, where the sound synthesis is done via generative AI, but the playing, the composition, all the fun stuff is still being done by the creative. We also wanted to explore the new soundscapes that offer diffusion, and also this new way of generating sounds. Another big motivation is that often creatives are in legal struggles because they use samples from other songs or maybe like from sound libraries, and this could be also a way to avoid these conflicts. So for related work, during our conception phase, we looked around what is similar to our idea, and we found that there's already a system existing that almost does the same thing. This is called Vroom AI and was developed during the neural audio plugin competition hosted by the audio programmer community. And it has less models than ours, and also no really options of settings or parameters. I'm going to show later that is in our product. Also, the resources from the community are really great in developing our plugin. So now for the background. First of all, synthesis. So synthesis is the generation and manipulation of musical sounds through electronic voltage. And the synthesizer is built of three main modules. So the source, where the sound comes from, in our case, is going to be the generative AI. The controls like a keyboard or knobs on the instrument, and modifiers that shape a sound. One of the most common modifiers is the so-called envelope. And there you have settings for the attack, decay, sustain, and release. So the attack is the time that it takes to reach the peak level of the sound. Then the decay is the time that it takes to go to a sustain level, and the sustain is maintained until you let go of the key, and then the release time is how long it takes to go back to null. To the diffusion process, so this is the generative AI that we use, and it has this inspiration in thermodynamics. And it's a process to train a machine learning model to seemingly generate images from random noise. And this is done by iteratively adding noise to a training image in the forward process, and then in the backwards process trying to learn to remove that noise. This is normally happening on a 2D pixel space, but with latent diffusion, that space is shifted to a latent space, a so-called vector space, resulting in less computational heavy training and a faster inference, and also allows the inferring of the model via text or other modalities. Well, how does this translate to sounds? Well, you can treat sound as an image, a spectrogram. In a spectrogram, the frequencies of sound and the corresponding amplitudes are drawn against the elapsed time, and then they show the relation of different harmonies and define the timbre and sound characteristics. And these relations are the reason that notes from different instruments in the same pitch sound different. To now generate a sound, you can train a diffusion process to generate the spectrograms, and then in the end translate back into sounds. And this is the core idea of the diffusion models that we used, Audio LDM and Audio LDM2. There are many other sound generation models. This graph is already probably outdated, And some make whole sequences of music, some are specialized in voice generation, and a few of them are specialized in sound generation. We chose audio LDM because at the time it was the most advanced and the most easy one to use across different type of devices. So both models were trained on a huge amount of audio data, and they're enabled to generate a wanted sound from a textual description. Both models use a latent space trained from spectrograms for the diffusion process, and in the second iteration, the conditioning of the model was reworked, enabling more input modalities and training with unlabeled data, promising better translation from these modalities into sound. Now to our instrument. The idea behind our instrument was to use these pre-trained diffusion models and build around them our digital instrument. We chose C++ as a language to achieve the minimal latency needed for audio programming, together with the JUICE framework and established C++ framework for programming audio plugins and synthesizers. To generate the audio signal from the C++ code would have been the most optimal to convert the pre-trained models into a binary file, but sadly due to the complexity and the use of different submodels, this was not feasible. And thus we opted to develop an inference service fast API in Python that the interface connects to and then generates sounds. So this is the resulting interface. I'm gonna demonstrate it live. So in the background, I have the diffusion server running. So now if I drag it in, I can open it. Yes. So down here you have first the selection of all the different models of audio LDM1 and audio LDM2. And then you have the option to choose a device. This is the torch device, and depending on your system, you have different options. If you have a Windows laptop or a computer with a CUDA-supported GPU, you can use CUDA. If you're on Silicon Mac, you use MPS, and in other cases, you have to resort to the CPU. So in my case, I'm on Silicon Mac. I will use MPS. I will initialize the model. Take a while. All right, now it's initialized, and here I can define the prompt that I want to hear. For examples, I will input warm strings. And you have the option to define negative prompts, so descriptions that you don't want in your finalized audio. Here you have the option to set the audio length. This is the number of inference steps, so these are the diffusion steps that are taken in the process, or the number of it, and also the guidance scale. The guidance scale tells the model how well it should adhere to this description. So higher guidance scale is a more strict correlation between the prompt and the final audio. I will change it to 4. And then I can generate my sample. All right, so as a little nod to the latent space in a spectrogram, I also included a spectrogram here and the waveform. And now you're also able to set the attack, sustain, decay, and release of the generated sample. There's also the option to tune the sound, because you don't know in which pitch the resulting audio is going to be. And to have a correct MIDI mapping, you can then tune the generated sound. Also, you have the option to make it louder or quieter. So now if I take the keyboard, I should be able to play some sounds while not hearing it. Ah, yeah. Thank you. So this is the turn down, sorry. So this is the interpretation of the model for warm strings. It may sound a bit weird, but I'll come to that later again. So in addition to the development of the instrument, we also conducted a very small study consisting of 6 participants with varying degree of knowledge in music production. And we posed questions about the quality of the sound and how well the generated audio matches the input prompt while changing different parameters but having a constant generation seed. One parameter is the torch device. As I already told you, it's depending on the system you're on, and from this we found that if everything is consistent and you change the device, the sound is changing, so there's no consistency in that. The guidance scale, we found that the most optimal value is around 4 to 5. For the diffusion steps, we found that a higher number seemed to deteriorate the sound and accuracy of the prompt, and this could be attributed to the fact that adding more information to a fully generated image yields no additional value, merely supersedes existing details. And the observed sweet spot, depending if you want a higher accuracy or sound quality, lies between 10 and 50. For the duration of the generated audio, it seems not to affect the quality or the accuracy too much. But what I personally observed is on longer audios there was this pitch shifting or pitch drifting over time, but this could very well be a desired trait based on the sound you want to create. The more interesting part of the study is we tested different scenarios for music production. The first thing that we tested is we wanted to generate single audio events, for example a single kick drum or a single snare hit, and in that the models did not perform so well, partly because of the training data, and this training data was most of the time repetitive music, so that has no chance of comprehending what a single event is. Surprisingly, some simple effects like adding reverb or delay worked, and also sometimes emotion or mood seem to work. Specific sounds or instrument, for example an 808 kick drum, did not work so well, so my guess is that there's more training data needed to train on specific audio production terms and context. And this is what I want to embrace also in the discussion. I would say at the moment the models are not good enough for precise synthesizing and more suitable for sound exploration. One can embrace the weirdness and randomness and from that craft unique sounds. Also, a nice fact about sound is this way for giving the images. A generated image with weird fingers or artifacts may be conceived as uncanny or weird, but sound can be further sculptured and transformed to effects and filters. An improvement to the models may be to fine-tune them. I don't know if you are deep into diffusion models, but there's a trend of fine-tuning the models with image of oneself or in a specific style, and then the model has that specific style. And a huge amount of audio engineers have their own sample libraries and could very well fine-tune the models to their likeness and approximate the model to their specific sound. Also, one drawback is that the model output is only existing 16 kilohertz. 44/1 or 48 kilohertz would be way more favorable. Then also, the sampler that we built was very rudimentary. So as already stated, we couldn't convert it to a binary file. So the packaging has to be the VST or the executable of the plugin and also this inference server. Thus you have to have a bit of knowledge in the command line to run the server, and I think many producers don't have that. And also one drawback is there's no loop points in the sampler at the actual moment. So normally in a sampler you can set like there's the starting point, there's the end point, I want to repeat that part that is missing. And most common samplers have that. And also an automatic tuning would be very nice. All this begs the question if implementation of a sampler is really necessary. One idea would have to be to have just an interface for generation. For example, like Stable Diffusion Web UI or Comfy UI, and solely concentrate on the generation, not the playback. And then in the end give the user the possibility to drag and drop their sounds into audio production environments or even outboard gear. Speaking of outboard gear, also an option would be to go the hardware way. Many musicians prefer knobs and tactile feedback, and it would be very well possible to build a physical instrument, for example with NVIDIA Jetson. I already tried if the models run on that, and they do. And then one could add keyboards and knobs to build a hardware synthesizers on which this process could take form. Besides the quirks and flaws, you are still able to generate usable sounds, and they may sound alien or weird, but in the spirit of Bob Ross, you can embrace those happy little accidents in music production to make something great. And if there's some time left, I could very well show this. I go back to Ableton. So last night I tried to build like at least one loop with different instruments, but because of this random nature of the instrument, it's very hard. But still I found something usable. So first of all, let me turn off all the effects. I also, for this, I chose the prompt warm strings. And I got this sound. I don't know about you, but that reminds me a bit of like jungle music from the 2000s. So I thought, let's go that route. And with sound effects, I came up with this sequence. And then it had to have some drums in it, and I simply inputted jungle type drums, and I had like an alright result. I had still to quantize it and to chop it up, but yeah, it's usable. Yes, so I would otherwise like maybe use it for some sounds in a composition, but not try to do a whole composition with it. And if you want to try any other prompts, feel free to do it now if you have a nice idea for a sound. Any ideas?
We'll have time for one or two of these.
Sorry?
We'll have time for one or two of these, and then we have to move on.
What?
We will have time for one or two of these,
Okay,
and
sorry.
then we will have to move on.
Okay, perfect. Crazy? Crazy ducks? Okay. All right, let's hear what crazy ducks sound like. I don't know, like, not so much ducks for me. Something else, maybe? No, this is only for sound synthesis, yeah. Backwards trumpet.
But in this sound generation, you could end up using these for like wavetable synth, or like you could set up an entire synth out of it.
Yeah. Yeah, so it has the notion of backwards, but yeah, I don't know about trumpet also.
All right, we should probably move on to questions.
All right,
Let's thank the
yes.
speaker.
So,
We have time for one or two questions, and it would be best, Stefano, if you don't mind to set up while we're doing that.
Thanks for the presentation. My question is about the training set. I don't know if you mentioned or if I missed it, but as far as I understand, the output
to avoid hallucination is very sensitive on the training data. What's the training data so far?
So I didn't train it myself, it was pre-trained, but I think it's from an online library of free sounds. So it has like some notion of music production, but I think it like a company like Splice, so any of the like big sound libraries would take that into hand, could like create decent outputs. Yeah.
I have a question while we're just getting the next computer connected.
Mhm.
If you ask your model about pieces, does it generate instruments characteristic to that piece? For example, if I typed in rite of spring, would I hear something that sounds like an English horn but is in fact a bassoon?
I would assume not so much for whole composition, but funny enough, like I tried some different artists. For example, I once tried John Carpenter an analog style synthesizer, and it had some characteristics. Some composers, I would say yes, but yeah, still for some distinct sounds, not whole pieces.
Cool, thanks. Any last questions? Then let's thank the speaker again and get ready for Stefano.
Yeah, I will.
Sounds like we're ready to go. All right, Stefano, take it away.
Greetings everyone, I'm Stefano Panelli from Alessandria, from the Conservatoire of Alessandria. I have a bachelor's degree in electronic music, and I'm soon to be like master's degree in electronic music. Today, I will showcase to you my own technique of making generative soundscapes without using AI. So basically, I know it sounds like funny today, being like having this much of artificial intelligence. But the thing is, I choose this way because it is basically my journey from Super Collider to Max MSP. And so that's how I learned how to make generative stuff without using any like high-tech solutions. And so I will start with a little demo. Mind that it will be in mono, but this method can work on like multi-channel or also stereo. So. So basically what you heard was like all synthesis and all totally generative stuff. Nothing is prepared before. What I'm showcasing today is my own techniques to produce something like this, to create, to engineer the actual patch. And those techniques can work in every audio and audio processing and synthesis environment, also hardware. Basically, I've set up 3 sound generators that everyone has a stereo output. Let's start with the first one. First audio generator is like a hybrid sampling ring mode generator. I will go quickly through it. There is 128 oscillators, like sine wave oscillators, that are being multiplied by one another, like the first by the second, by the third, etc. And these having like some beating frequencies in the oscillators makes a really kind of rhythmic and kind of randomic signal. And I sample these in real time and use the sample to produce various parts of my generator. For example, the bass is from the sampling, the ambience is from the sampling, etc., etc. Second generator is based around wave shaping and confiltering. If you need, I can open. It's like some kind of freestyle stuff with Gen. Basically, I discriminate between upward going cycle of the wave and downward going cycle of the wave. I took inspiration by clip synthesis by Maurizio Giri. There's synthesis techniques that basically divides the audio in positive spikes and negative spikes, and you can run different parts of the signal in higher, like higher than 0 and lower than 0. And then it goes through resonance filters. The third part, that is the most complicated one, is basically also ring modulation synthesis, but with resonant bandpass filters to amplify the basically the clicks that ring modulation synthesis produces. The like special thing about this method is like basically in the control layer. I selected some parameters in the sound generators blocks, not to be totally randomic, but to have like some macro functionalities, so I can basically manage multiple parameters in one go. And then I use this technique that is basically this kind of stuff. I have a random generator, a low-frequency random generator that maybe in hardware you can low-pass white noise, basically. In Max MSP you have a handy function that does this. And then I use basically a comparator to generate banks and to update another type of values. This system makes me basically control the speed of my ambience, as written here, coarse speed randomization. And also I can use if I choose the right parameters, I can link those parameters like with updates also in some other environments. For example, imagine if you are building an audio system, for example, for a video game, not in MSP, or for example in a audio installation, you can leave some parameters to basically other stuff that can run in the installation, for example, people triggering sensors and stuff. And also, I have the same principle applied to the output of my generators. My approach to this is based around dividing my patch in blocks. I have a control layer, I have a sound generator, and post-processing. It's like a way of thinking before and during the designing phase to have most of the decided before. So you have a really nice control of your signals. And then you go into the post-processing part, that is basically the managing of the audio output. And every couple of signals that outputs from the generators are sent to a VCA block that is controlled also by the randomic signals, just to basically make the volume change for the separate channels. Basically, it's like I'm running the mixer of it. And also, another type of block that I usually, or layer that I usually use is, I call it an analysis block. Basically what it is for example, I choose a parameter of the audio I'm outputting. In this time is amplitude, and I run it to a comparator. And I manage the output to the effects block. Effects block right now is a reverb that is managed with this kind of analysis type. And also I randomize the value for each reverb, the room size for each reverb. Other stuff I could look. I took out the control layer and out layer speed just to show you how they interact with the patch. So basically, the higher the value, the faster the events are gonna happen. So if I run, you will see that each parameters basically have a different speed based on these values here. The higher this value, the higher the speed, and the higher the change of the events. Right now, because as I said, it's stereo and it's not mixed to mono, so and basically that's all in my technique. Something else you can implement is, for example, feedback. You can implement some cybernetic stuff. For example, the managing of the feedback amplitude through amplitude, basically monitoring. You can look at frequency output with a frequency, how is it called, the frequency detector. Like the technology that is used in tuners, for example. If I output 100 hertz, something happens. If I output 200 hertz, something else happens. So this type of conditional stuff really helps with this kind of functions. The thing is, every time I will open and close a patch, the output of the patch really changes. And also is like a way to generate samples that never repeats. Higher dynamic range than the usual. For example, other goals for this type of project, for example, as I said, is like situational sound design, for example, in programs like UIs, or I can imagine it working on cars, for example. You can have a generative type of sound engine that works on the sounds in the car. Right now we have like a sound for electric cars. You have I don't know how it's really called. You have a sound that makes people hear you, because the electric cars doesn't make actual noise. And you can use these type of methods like parameters managing to make this kind of sound, to make it more natural, because right now they use sampling most of the time. Or for example, as I said, you can use it in art installations, and link the parameters to whatever you like. And so basically the possibilities are endless in this kind of method. The thing is more like a way of thinking when you are designing than actually like really new techniques. And so that's all. If you have questions, feel free to ask. And thank you for the organization to choosing me for this presentation.
Thank you so much. Lots of questions for Stefano. We will start with you because you're going to have to set up soon.
Did you implement at any point seeding for the random objects? Sorry? Did you implement at any point seeding for the random objects?
The way I implement seeding is not like using actual seeds, but if I want some parameters to be linked or like relative to each other, I usually make some permutation to the randomic signal instead, because I prefer it to give more than a seed. I usually had to work with seeds more through AI than this kind of stuff. You? Oh, okay.
Right here. Hey, first of all, this is great. The user interface, the being able to deepening to any of the boxes, this is a wonderful UI pattern. We see this over and over in generative solutions. Have you ever played with Grasshopper as a plugin for Rhino?
No.
Have you ever played with Bitwig and its grid?
Bitwig,
modular
yes.
synthesizer?
Yes,
right, they both have the same notion just as you showed. Like I can have widgets on the screen, wire them up, and then go deeper, and then go deeper, and then go deeper. That really has a lot of power, and seeing that play out, and this is really something. That's why I was wondering how much inspiration you pulled from those other existing sort of UI methodologies of this sort of abstract box towering.
Okay, actually, my inspiration for this comes from basically having to do with hardware, because the way I usually make patches with hardware is like having this way of thinking. So I think about some parameters being used in a synthesis or like sound generator, and then I implement. So how can I move these controls? How can I move this set of controls without using my hands? Because basically what I do like in a like creative environment, I like to watch the machine more than like putting my hand in it. Because sometimes the machine can have I know it's weird to say, but it can have really nice, almost real life-like characteristics. Also in analog, feedback is not implemented like in digital. It's being.
All the time we have for questions. I'm sorry. We'll have to take the rest offline.
Okay, sure.
But Stefano will also be performing this evening in our performance evening.
To go to the sound.
So you'll have an opportunity to hear a little bit more. For now, let's thank the speaker again and go to our last talk.
Thank you. Can I unplug?
I also should say that we're going to go at least 15 minutes, likely longer, into the break. So if you need a quick dash for water or something, this is a good time to do it.
I think it's. I don't know. No, he was wondering who is this? Who? From who? Okay.
All right, let's see. Hello. My goodness.
Do you need to do a quick sound check for your computer, or are we all set there?
Let's start with this, and then we just move really quick to the sounding part. I know that we are, oh my goodness. So, okay, in the sake of try to go to the practical part, I'm gonna just read through the abstract and then go straight to the thing, you know? So you have like a whole idea of the thing. So procedural music generation in video games is rarely used in development despite its potential support for interactive narratives and falls beyond broadly used procedural methods like graphic management. Currently, developers rely on pre-produced audio sequences focusing on sound quality while balancing storage and variety. Techniques like layering and resequencing are standard through sound design platforms like F-Mode and Wise, allowing adaptation and interactivity in gameplay. However, this can lead to repetitive audio, which becomes particularly noticeable in extended gaming sessions, diminishing the impact of musical storytelling. This study introduces the Progressive Adaptive Music Generator, PAMG, an algorithmic system that generates continuous music streams based on gameplay variables, seamlessly transitioning between moods, styles, and tension levels. It includes motivation, theoretical framework in the field of generative music, overview of the system structure, and a preliminary implementation test involving a trial game that compares conventional implementation with PAMG. In the discussion section, I address test results and issues and future work. The study reveals a preference for PAMG music over traditional methods in certain aspects, although results are not conclusive. Okay, so basically this machine does is making music in real time and uses some parameters that you're going to see here that come from the video game. And so the video game can control whatever is happening. You can assign that to any kind of variable that you have in your video game. For example, if there is a guy, like a really bad guy that is just chasing you, you can modify the tension according to the proximity. Yeah, so it gets like more tense the closer it gets to you. Yeah. Okay, let me show you. I'm gonna switch over here. So I'm gonna. Oh my goodness, I don't want to give you my back, but hello. Ooh. All right. So this over here is the let's say the flow chart of what is happening. The first section is how it generates the pulses. The pulses are like the basic ingredient of everything like here. You will see the pulses going from here, from left to right. We're gonna try to see how it works here. So we have an agent network that is gonna produce all the musical events. We have a melody agent, a harmony agent, and a percussion agent, and an orchestration agent. The three main agents are these. This is the melody, the blue one, harmony, and percussion. Each one of them has a set of parameters here you can modify. The idea of how this is supposed to be progressive is because every one of these parameters somehow is getting something more complex or tense when I go up. Yeah, that is, I mean, whenever you read the paper, you're gonna see that I may have been even overshooting the references for that, because complexity and tension are concepts that are really, really deep in music to study. Nevertheless, this is like one of the implementations that you may see, and is, of course, framing to the Western tonal music to make things complex cognitively somehow within this kind of music, maybe the style anyway. Then what you do is that there are presets that are assigned to these corners in the lower part. You see it here. So let me show you a couple of things that happen here. I'm gonna do a reset. So it goes there. And then these XY pads are having each corner has one particular style. At this point, in the lower left corner, in all of them, there is a style. Then if I move to the other corners, it's going to interpolate between the parameters. If you see all the parameters are moving, yeah, depending, and like fitting until the point in which they resemble this one here is this one, you see? This is the melody agent. This allows for a transition that goes from one style to the other. Okay, let's see. Well, the orchestration agent is around here. Well, you cannot see it like quite well as like an agent in the user interface right now, but what it does is assigns the instruments to these four families of instruments. Well, the piano is by itself. We have strings, we have piano, we have woods, and we have brass. And well, let's continue to see what can we do with this. So the melody agent, this in some ways the director of the timing and is the creator of the rhythmic patterns. So there is something that it produces that is the list. I call it like the move list, because it starts like the most simple version of a rhythmic pattern will be just, you know, going with the beat. It's what you do with, I mean, if you try to make a kid follow like the most simple, like repeat what I'm gonna do, it's gonna try to follow exactly the beat. If you go a little bit further, then you introduce some kind of syncopation. So what I did is to move them either forward or backwards to increment, like slowly, the complexity of the rhythm. Yeah. So it produces a list that is already with some kind of syncopation. Then that list is going to be affecting what the other agents are producing in terms of the onsets. They, however, can decide to disagree with that and go a little bit to support the meter, the accents that are produced in the music. Okay, so let's, let me see, well, okay. So the first thing that it generates is a list that is an indexed list with two different properties besides like the actual index. That is the duration and the staccato legato property. So it can be staccato or legato. Then it sends the duration directly to the, like basically the music production. Velocity, I want to say a couple of things about velocity, but then, well, let's continue with this. Then there is a section that produces the pitches. The pitches are produced basically with two types of algorithms. Two of them are basically the random walk, that is like a drunk object in Max if you have worked with that. The drunk object, I had to recreate it because it doesn't produce the same result with a seeding, and I need the seeding to produce like something that you can recall. That is part of how we recognize something as music. That is not just, you know, well, of course there is like an stylistic way to do music that doesn't repeat at all the time, and it's possible to do that here also with the seeding that is 0. So that is also possible, like it's kind of, okay, you know, improvise on things that are here. Then it works with a harmony. So the harmony, let's go to the harmony. The harmony agent has two functions. One is to produce the harmony, like the grammar for the harmony that is going to be employed. And the other is to produce chords. So it has like a sounding property, produces chords, and it has two ways to do it, like a chord itself or with an arpeggio. So it generates at some point an arpeggio to, you know, balance whatever you're hearing. It uses, at this point, it's using a chord dictionary, and those chords are hierarchized in a way to add tension to each one of them by adding one by one each one of the pitches. Let me see if I can show you a little bit of that. Okay. I am going to take this out. parameter, I can add, if you notice here, more onsets. At this point, it's doing an arpeggio. And I'm going to make it more tense. I don't know if you can hear it, but effectively it's getting more tense. And if I go here, you see here 12? That means that we are effectively dodecaphonic. So basically non-tonal. So at this point it's quite tense. If I can say something like that. But there are other ways to make it more tense. Let's say I go like around here. And this is a complexity for the progression. So in this one, what is going on is that the progression is starting to have more sections with different kinds of grade degrees over the original tone, the tonic, and also has the possibility to modulate. Like a bit of music, maybe you understand what I'm saying. So I can go even, yeah. Let's do something like the most tense that it can be, just with the complexity of the. You're gonna see some secondary dominance and some modal exchanges and stuff like that all over the place. If I pull all of them up, of course, it's gonna be far more complex. There are other parameters that we know in music. There are, for example, range. You see here what it's producing. The range is extending the range of what is produced. You see also the register can be up. I can add or rest instruments with this one. Just one instrument. So just woods at this point. Then I want, let's say, one more staccato. Let's see, I want that in maybe strings. Let's go back to something a little bit more simple. And then, for the percussion, okay, so something that happens, about the complexity of the rhythm. As I was telling you, this guy here is what produces the move list, which is like the main pattern for the rhythm. They can decide to adhere to that or not. At this point, is this one. So if I put this higher, you will notice that there is some syncopation here. It's trying to adhere to these points in the melody. Oh, I forgot to say, there is a contour parameter that makes this kind of line. And there is another kind of shape that is like long-term for like going up or down throughout several measures or loops that I call here. Okay, let's go a little bit further with the percussion. Let's see, okay, the percussion. point is following the syncopation. At this point, when I put it down, it's not syncopated, so it's kind of like a marching band. Here is for the kick and the snare. These are the two of them. And check this out when I put it. Yeah. This is trying to follow the mood list, and this one is trying to follow just the basic beat. I can do the same with the toms. More toms. Of course, the more onsets is also part of like making more dense and possibly more complex what is happening. All right. Okay, well, the orchestration, as I was telling you, is in charge of moving a little bit the voices throughout the instruments. And is in communication with other properties like the arpeggiator, because it's trying to follow some idiomatic features that some instruments cannot do with the arpeggio. The presets work, as I was telling you, as a set of them that are assigned to the corners in each one of them. Then there is also, so the main thing on how to generate things that are a pattern that can be recognized as music is the seeding in all this. The seed produces a sequence that is exactly the same as before. And I can call several seeds if I need to increment the amount of material that you are hearing. Yeah. Also, I can use a seed for a sequence of seeds, if that makes sense somehow. So that also can be recalled, and then you have several sequences that can come back if you need to. Okay, I think that is that for that. I wanted to mention something about the test. So I did a test. I checked with some students how to compare this kind of music that is generative with music that is normally like the conventional way to create music for video games, that is basically a segment of music that is put there and is triggered. Sometimes it's layered, sometimes it's resequenced. Yeah. So, well, there is the comment that people say, like, you know what, I've heard this music so many times that I have to mute it if I play video games a lot. So he was like, well, you know, that is, and I found the studies. There are some studies that talk about that. And it's curious because they say, well, there are two ways to listen. One is the direct way to listen is like, okay, you close your eyes and you listen to whatever is the music. And then how many times you have to listen to be saturated. If you do that in a focus, it's like 8 times, one at a time. If you, like music that you love, you have to listen to that 8 times, one after the other, and you say, you know, I'm done. Yeah? But if you're playing something or it's in the background for a video game or for a movie, you can listen to that like almost like 32 times before getting saturated. So that's why this kind of thing that it's been around for a while is not taking over video games that easy. You may say like, okay, I mean, why is not something interactive or reactive to a video game more implemented like in general? I think it's because of that. But anyway, I decided to do the test to see if people can say, okay, this is better or not, or they don't distinguish, or, you know, whatever. So what ended up happening is like this. Well, first of all, with the, you know, the ANOVA test got no significance in the real thing. Possibly because it's also too low. The people that play the game are not too many. Maybe if I do a more extensive test, it will get more results. Nevertheless, in all of them, PAMG was better than CBI, clip-based implementation. And these are the results. they had to score the music of the two implementations of music, either with is better, or is slightly better, or is clearly better. Just two, or no, I don't find any difference. So basically 3 different categories of that. The score is from 0, 1, and 2. So for the first graph, it's from 0, 1, and 2. That is the average of all of them. And it was better still for PAMG. And now, by group, you can see that there is something happening here. So that is another problem with the test. I didn't employ a test for priming. So what happens is like this. Whenever you have to play here, you're going to see that, okay, I need to, like, I put my brain to try to play the freaking game. You know, I have to, you know, solve the dynamics, the mechanics of the games and all that stuff. So I'm not paying attention to the freaking music. Then when I get it, I can, So in general, most of the people are grading better the second music because they already have figured out the mechanics of the game. Yeah? Kind of a problem. But it's more or less proven by this. Okay, I think we are ready to play. Who wants to play? Well, give me a second. I'm going to check if the game is working. I'm going to have to do something here first. So the game has already the two kinds of music working. This one is the music that is like in the traditional sense. And if I move it like this is the music generated by the machine. At this point is real-time generation. The other one was, so if I go back, you're gonna hear the same thing. Isn't it? Let me check if I can. I'm gonna quit the game for a second. Then it's ready to play. Come here. Let me put a little bit. Anyway, let's try. So you can see the instructions here. You're gonna play with the mouse to be able to play. It's a first-person shooter, so if you have so you can start the game. This guy you just shoot. Find the cube. Right. Yes, there. With the, yeah, there. So there are some portals. You're gonna find some portals, and the portals are your friends. They replenish your energy. The bad guys don't die, but when you hit them, they are slower. They are faster than you if you don't hit them. He's losing health all the time, so he gets like, do something, try to find the freaking. With the water. You can swim, but if you go too deep, it's gonna lose energy faster. Let's do another try. You wanna play again? Whenever you get to the portal, you can see through the portal where you are arriving. So check if there's no like a bad guy just lurking. Higher when the bad guys are closer. Go with that arrow. All the way. Good job, good job. Run, Forrest. There, go. Continue. Yes, further. Got it. One, very good, awesome. All right. Hello, hello. All right. Let me put this thing away. Okay. So that was what I was telling you about the cross thing, that was a little bit better if you had the game in the second group. And then, yeah, of course, this is open for development. If you want to work with me, just hit me up. I am ready to do more things with this. The next step will be, of course, like a VST. A VST will be super easy to do to have something generative that can be tied to MIDI and automation in a DAW. Super easy. And then making a plugin for Wise or for any of the engines, which will be really interesting. And I need people that know how to resynthesize samples and also analyze grammar from composers or something like that. Anyway, thank you so much. I'm in touch, whatever. There are many things to say. This is a far bigger work than it looks like. But I'm ready for anything. Thank you so much. Questions?
Names and illusions, so we can take as many questions as we'd like.
So I know I say this every time I ask a question, but again, amazing work. This goes back to something that I think all of us gamers have wanted forever. I remember going to an early QuakeCon after the Quake 2 release, talking to John Carmack, and they were saying that they wanted to do things like this in that time, in the mid to late 90s. And that was the era of EAX, 3D, and 2D, just stereo speakers trying to find some sound thing there. And they came up with some solutions, but they could not crack this. They could not come up with generative music where the tension would build as the danger went up, and things like that. And it was all the problems that you were talking about, and one more that I think hinted a little bit that we saw at the very end of the game, CPU power, right? The ability of the end user to be able to do all these great things that the game does, and then add this on top, right? Where they're really generating these things, whether parts of them come pre-scored or fully generated. So what do you see as a roadmap? Do you find that further optimization of this approach can get it to be embeddable, not just in AAA titles for people who have $10,000 machines, but also for the rank and file that might just play mid-range games or indie games, be able to have access to this running in those kinds of scenarios?
Yeah, well, as far as I've been working, this machine that you're seeing here is 2018. It has a powerful GPU, GTX.
Right? Compared to those 1998 machines, right? This is
a GTX 1070. This is, I don't know, orders of generations. This thing is not the best machine at all. Yeah.
So is the audio running on the GPU?
The audio is running on the CPU.
That's what I mean, though. So even though we've offloaded all these graphics, we're doing all these other AI pieces and stuff like that on the CPU. So can modern machines running modern games have extra CPU for all this channel audio? I know when I'm playing in my DAW and doing live synthesis, I can run myself out of CPU without trying really hard, and I'm not playing a game at the same time. I'm just curious how complex that is.
So the complexity for the CPU is not as much. So there are two things. One that, so for a video game, the efficiency strives in two things. Is storage, which has to do with the bandwidth to transfer the information, yeah? And the other is processing. So for example, it will be more processing if I had to do synthesis in real time. But
sure, but if they're not just sample playback, right?
These are samples.
Right, so that helps.
It helps, exactly. It needs some bandwidth, but it still is less than what you normally get with a video game, because also it has to do the sound design, some other effects, and sometimes some actually real-time effects in the platforms that you are employing for the video game. So this one is actually not that bad. If you will do something like machine learning or something a little bit more convoluted, possibly will take a toll in the CPU or like the processing unit that you're using for the video game. So as far as it's right now, that is like an algorithmic model, I think it's max 7. That doesn't, I've been checking like the, how is like the processing, if it's like 100% or something like that. It is not. And this is an old machine. It's the 7th generation of
That's great.
Intel.
I'm so happy you're so bullish on it. So yeah, anybody who wants to work on this, get with them. Let's see this. I want to see it in many, many more games. Yeah.
Thank you, man.
So I have a quick question. As you were alluding to, when this started becoming popular again in like 2002 to 2008 or so, people...
Can you speak a little louder? Sorry.
I'm very quiet. Somewhere around 2002 to 2008 or so, the idea of computational soundtrack and scores for video games was getting really popular. They tried doing this. It sounded pretty bad, and because they didn't have your paper yet. But what they seemed to settle on was a bunch of pre-composed segments and crossfading between them. Sort of like, weaponize minimalism so that you can end the piece whenever you feel like, even though it's pre-composed. Do you see any role for integrating the sort of pre-composed crossfade paradigm into your generator?
Yes. So one of the things that is, as I was telling you just a second ago, if you are interested in working with me, I am completely down to it. I want to make a plugin for a middleware that is called Wise. Anybody knows about Wise? So Wise is the middleware engine that sound designers use to implement sound design and music for video games. What it does is that it can resequence and layer things in music and also in sound design to avoid that things sound exactly the same when they are triggered. So that is the way that it makes like, okay, I know that every time that I shoot, it's not going to play exactly the same sample because, oh my goodness, it's exactly the same. No, it has some random range in which it fluctuates, and that is a way to make the thing more bearable. Those things are already implemented, yeah? And a lot of the music has been using this kind of approach to avoid being like, okay, it's completely typical and stuff like that. Nevertheless, you still hear the same samples. It's not that easy to just, let's pitch shift something like an audio sample or a music sample, yeah, in this case. To just pitch shift it is not, it doesn't sound natural. It's not that easy. So what they do is to put layers on top of that. I couldn't show you a little bit more of the CBI because I employ those layerings to try to do exactly the same as I was doing with the other one, but with a conventional approach. I went last year to the GDC, the Game Developer Conference, and I talked with many people about this, like why the hell is this not taking over video games? It's like common sense, it should be better, like I am not like a genius that is going to employ something that no one has. Yes, everybody has thought about it, and some games have it, but they employ like the Spore. Anybody played the Spore? The Spore has some generative system that makes music in real time, yeah? But there is nothing like general that you can, I'm going to use this engine for this game and for another game or for whatever you want. So what they say is like this. It's better to have some quality, and also the composers know how to use a modular approach to composition, like how to compose music modularly, so they can put like this module will articulate with this other module, and also can overlay with this other module in terms of the harmony and the like whatever they want, and then they can make things more complex just by overlaying things or resequencing things. So they say like, you know what, we have like the tools already, we have the people that know how to work with this in the way that we have been doing it, we don't need to create something different. And the problem is that if you want to disturb that market with this, it's going to say like, so the composer is going to say like, well, I already make good music with the system that I'm doing, I'm getting hired by this.
why should I employ this kind of other approach? So there is a thing. What I need to do to make them use this is to be able to gather the grammar of the composer to make their music interactive. Like somehow analyze the music that the composer already made to make some music that is part of the grammar or the style that the composer did, but then make it interactive.
Did you think about, because a lot of the video game music I grew up with, like, motif is king. And I was wondering if you thought about that at all, because there could be like a theme that's like doo 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 doo, but then in another part where it's like dangerous, you hear in the bass, you're dun 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 dun. It's the same motif again somewhere else, and that brings the unity to it. And that's what composers provide that often generative music just misses out.
Completely. So maybe I mentioned a little bit what I'm doing for creating those motives, and like motives either in rhythm or in melodies or whatever you want, is by doing the seeding random number generators. There are other ways, and also there is a way to say, okay, you know what, let's use a melody that is already done and then vary that melody with some of the procedures that I have there that are kind of simple. They are not like super difficult. There are other ways that we can improve the generation of the harmony, that maybe with Markov or something like that. Those things are really easy for computers. It's not that difficult. But yeah, I mean, basically the melodies or the motifs that you can create are handled by like calling that back with a seeding at this point, is what it's doing.
And with that, I think let's thank our speaker one last time. And that concludes our regular daytime program of Farm. Thank you all for coming. You know what I'm about to say. There's a performance evening tonight. It is at the Auditorium San Fedele. Thank you. And the time you should get there is 7 p.m. You're all so good. It takes 30 minutes to get there. Metro. Walking takes about an hour. You can walk if you want to, but there are rolling thunderstorms, so just be ready for that. I believe that those are old imperial minutes, so they're the minutes before the changeover sessions in the 1850s. Right, well, thank you all for coming to Farm. It's been wonderful hosting you, wonderful seeing your work, seeing your appreciation for this work, and I hope to see you at another Farm again. Thanks, everyone.